Não seja o microfone lá. Okay, morning, everyone. Dear colleagues and the students, both here and outside of São Carlos, maybe so many students in Belo Horizonte, where we have our meeting, which starts tomorrow, in the other parts of the Brazil. It's my pleasure to introduce Professor Francisco Antonio Macías Domínguez, our teacher on the course, The Use of Allelopathic Studies in the Search of Natural Herbicides. He earned his degree in chemistry from the University of Seville and his PhD from the University of Cádiz, where he is now a full professor. He leads the Allelopathic group of Cádiz, the first research group in Spain and Europe, dedicated to this field, focusing on discovering natural compounds to regulate plant growth and the interactions. It's very, very important and very long. Professor Macías' research aims to learn from nature to develop the environmentally friendly herbicides and insecticides. Currently, Professor Macías serves as president of the Phytochemical Society of Europe. We would especially like to thank the Natural Division of the Brazilian Chemical Society and to the students who became involved in the organization of this course. Finally, we wish you have an excellent course. Thank you for your attention. Now I invite Professor Macías to start your course. And about 10:30, 10:30, you can give a break for a coffee.
Okay, I'll try. If not, you just make a signal, okay? Okay, thank you so much, Fatima, and thank you to all of you for coming here, and also the one that is attending outside. And I hope that to see you, more of you, also in Belo Horizonte from tomorrow morning. Don't forget, my lecture is going to be the day after tomorrow. So, well, as Fatima said, Professor Fatima said, I'm working since the last almost 30, 40 years actually on allelopathy. And I just try to show you from the early beginning to how complex could be, it depending on your intention and depending on about your curiosity. Because as a scientist, you must to have curious, and you must to find a way to produce any kind of ideas that you are imagine it can be possible to do it or not. You will see. And my first message is simple. Please don't accept impossible. Everything could be difficult because we have not the technology by the moment, or we can have not the ideas, completely clear ideas at the moment. But if you are not dreaming in bigger, you never can go. And science is growing up because the dreamers, and the dreamers are you, okay? Well, let's start. Why I'm working on allelopathy? When I finished my PhD, I was working in traditional, let's say traditional way of natural product chemistry. And the traditional way of natural product chemistry was very simple. You can imagine. Some people advise you and say, okay, this plant is excellent for a headache. So, oh, wonderful. So I go to the field, I take the plant, I take 20 kilograms, 25 kilograms, I dry it and make in a Soxler, I make extraction in heating solvent, and then I start the separation just by column chromatography and so on, step by step, but no biological test was done by that time. Only chemistry, means only separation, normal separation. So at the end you have something in your hands, but you really don't know exactly what is this. This is the real active compound, the real active ingredient, so you don't know. So when I finished my PhD, as I mentioned, I was starting working with 4 different plants belonging to Centaurea canariensis, Centaurea different ones. Was from Canary Islands, some of those, and other for the peninsula of Spain. And we isolated many compounds, but during those compounds also a collection, a special collection of sesquiterpene-lactone. That's my, my favorite, sesquiterpene-lactone. Sesquiterpene-lactone with a special functional group. They have an oxetane group. You remember oxetane comes to your mind maybe Taxol, because Taxol has the oxetane. Yes, I describe for the first time in life the first sesquiterpene-lactone with an oxetane ring between 11 and 13 carbon. Was really very, very important and difficult, by the way, very difficult. So, as I mentioned, when I finish, I say, okay, I have my PhD. So what's meaning is you have a PhD? Meaning that you are free to ground your scientific work by your own. And this is important because you say, okay, you can do two things. One, follow one line, which is okay, or try to do something else. And I choose the second one, try to do something else. Why? Because I say, okay, the plants are producing some compounds, bioactive compounds, we call it bioactive compounds, but sometimes we really don't know. Because of what? Because of Francisco is taking care of the plant, Francisco is squishing the plant, Francisco is making isolation. Something is strange. So I was thinking in a different way in the natural product chemistry. And this is what I really invite you to do, is thinking about why a plant is producing something and why a plant is using something and what is the effect that is producing over the other different organisms that are living together at the same space and the same ecosystem. Okay? So it's changing the shifts, and we change for a new dimension in natural product chemistry. What is the main goal? The main goal is try to find what chemicals are involved in the communication, okay? What chemicals are, let's say, putting on the top, putting in the field, putting in the air or whatever. I mean, what is the mechanism of action of those compounds? The third one is, what is the real active compound that is going to the target plant, and what is the effect? I mean, what is the mode of action? If you have in your hands what chemical is there, what mechanism of action, and what is the mode of action, you have in your hands fungi, anti-fungi, antibacteria, anti-herbicide, anti-insect, I mean anti-feeding. You can do whatever you want, but natural way, in the natural way. Okay, as an idea, it's okay, wonderful. Why? Because allelopathy is a consequence of what? Of the oldest, because the oldest way of communication is the chemical communication within the living systems, okay? And this is really important. So try to know what kind of chemistry is involved in our relationship, okay? And then, because of the lack of mobility, of the plants, they need to grow up in the place where they are arriving. They are making a very sophisticated set of molecules and can be used in many different ways. And this is our goal, try to define what kind of molecules are involved and what is the mechanism of action, as I tell you before, what is the mode of action. Okay, I just try, first part, let's say, I try to do something about the state of the art, which is the meaning of the different concept of Allelopathy and what is the methodology. And then I will try to go to these two main, let's say, field. One is the non-manipulated ecosystems, so I will show you allelopathic studies on wild plants. And the second one is manipulated ecosystems, so I try to show you allelopathic studies on cultivated plants. This is part one, okay? So as I mentioned, the plants are really involved in many sophisticated interactions. But the most important are the one developed by plant-plant interaction and plant microorganism interaction. Of course, they have plant insect and plant mammal, obviously. Okay, and the science that study any process involving secondary metabolites produced by plants, algae, bacteria, and fungi that influence the growth and development of agriculture and biological system is the one that we call International Allelopathic Society, means allelopathy science. Okay, The oldest molecule and the oldest report that has been done about allelopathy was from Barnard jugulans nigra, Barnard, and the compounds is jugulon. It's a naptoquinone, very nice naptoquinone. I start with this and I will finish maybe this afternoon with this also, and some others relatives. Okay, what happened with the mechanism of action? To be considered allelopathic interaction, the compounds are produced by one donor plant should go through the media, means air, water, exudation of the roots or whatever. So you have different kind of potential mechanism. One is the volatilization from leaves. Second one is the leaching from leaves by rain, fog, dew. Releasing from decomposing leaves, fruit or twigs, and release it from decomposing slowly roots. And of course, what is really important is the exudation route directly to the field. Okay, approaches. Every science, every point of view are okay. So we are very related with agronomy, biochemists, physiologists, genetics, of course, analytical chemists, and why not, organic chemistry. I'm organic chemist. Well, let's see. I will try to show you some examples. Okay, this is allelopathy, an ecological science, non-manipulated ecosystem. I will show you baryons under certain trees in rainforests and Melilotus mesanensis. Means that you have some idea about the ethnobotanical, because they say the farmers also, they show you some ideas and say, okay, this plant is growing, but under the plant is nothing growing up. So you say maybe could be allelopathy, but sometimes it's just a competence. So don't need to be exactly allelopathy, okay? You have also, in this case, Centaurea maculosa. It is an invasive plant in much of the western United States of Canada. Oh, this is also a very nice plant that we call it Echium plantagineum, call it in Australia Patterson curls, because it was very nice. It is an ornamental plant, okay? So the people take from my province, from Cádiz, okay? Take it and bring it to Australia. But now in Australia is an invited plant. Unbelievable, really unbelievable. Very nice, by the way, this one. Okay, in the case of manipulated ecosystem, we are talking about crops. And you say, oh, manipulate crops? What does it mean? Is that, don't forget that when I do something against you, you do something also against me. So we have feedback, okay? And from this feedback, we can take advantage or not, or maybe we have not, okay? So in this case, we are very, very interesting when you have crops. And you have weeds within the crop, okay? What is the major crop that you can imagine in the world? The major crop comes from rice, okay? But the second one would be wheat, and the third one could be sunflower. Of course, soybean and maize and many others, but those are the biggest ones. And what happened? You must be sure about what is the, let's say, environmental condition. What are the weeds that usually are there, and what are the weeds that normally is making interactions. Okay, if you have this concept in mind, you say, okay, we can do some biological control, thinking on plant microorganism. So maybe it's a good combination. Sometimes it's working very well. If I apply one plant together with a microorganism, it could be a fungi or could be a bacteria or something like that. So the combination of both, you never know at this point. You don't know why, but it's sometimes working very well, actually. Okay, it's very useful for organic farmers, because they are not allowed to use, they have many restrictions to have something for control weeds, okay? Second way, okay, you have also allelopathic agents, not plants, but all allelopathic agents with microorganisms. This is more important and more interesting for me. I will show you in a couple of minutes why. Then you can work also in bioremediation. Bioremediation, when you have a contaminant, important contamination in the field, and you want to remove some minerals or something that could be very dangerous for the crop. So before using the crop, before using the land for growing something, you must to have bioremediation. So you have plants that can uptake those minerals and transform it, and also some of the, let's say, toxic compounds that can be out from the system. In this case, again, you have both combination. You have plant microorganism and allelopathic agent microorganism. And of course, to help in reforestation, when you have a big, let's say, damage in the environment, like a big fire. For instance, we have a very nice experience in Canada where it was a big fire and destroyed big forest, but then can be recovered. Usually it's taking about 20 years to recover the original, let's say similar to the original conditions, but now we can recover in less than 10, which is a real advantage, okay? And now with the climate change, the fires coming very easily and very quick every year. In Spain, we suffer a very dangerous fire in the north, in the center, and also in the south. Unbelievable, many hectares disappear, okay? So it is important to have a reforestation. Why reforestation? Obviously, because we need it. We need the plants to have a fresh and clean air to survive. Okay, what we can do also is to look for new models of natural herbicide, and this is the main topic of this, okay, of this course. In this case, we have the possibility to found something that could be involved in this particular ecosystem. And you say, okay, in this ecosystem is working very well. Can I make a translation of this system in a different ecosystem? It depends. It depends on the plants, it depends on the media, it depends on the field, it depends on many factors. But yes, that's the main idea. And of course, sustainable agriculture. So you can think about crop rotation methods on smothering crops. And it's working very well. Because sometimes you don't need to make a complete isolation of the compounds. Just know that the compounds are there. And you make enriched fractions or just residues. I cut it, the plant that I want to, let's say, use as a cover crop, and I can deposit here in the middle, and they can make free of new weeds for the main crop that is in the line. Okay, in the case of new model of natural herbicide, we can use the natural herbicide that we have tested or we have, let's say, make the discovery, or we can modify the structure, okay? And you can modify the structure in order to what? In order to make a structure relationship study and to avoid any side effects, and to improve also solubility, permeability, availability, and many other things that could be increase the positive side and decrease the negative side, okay? Well, in the case of sustainable agriculture, which is really important, the allelopathic plant in crop rotation play a very important role. Why? Because you can imagine, if I have a sunflower crop, okay, as soon as I cut the heads and I make a harvest, in the field you have many compounds that has been released time by time during the crop. And when I try to grow up something else on top of the sunflower crop, you must think about what kind of crop do you want. Dicots or monocots, dicotyledons or monocotyledons, because sometimes can help, sometimes can be damaged. So it's something to know why is the best way or what is the best way to make a rotation. This is something that in agriculture is very known, and all the people that has the potential to have intensive agronomy, they know exactly what is the best. But now we have a chemical phase, so we know why it's working in this way and not in a different one. Okay, you have smother crops and you have the use of phytotoxic mulches, cover, as I mentioned, and this is something also very important, genetic transfer of allelopathic traits into commercial crop cultivars. This is really important because we are not transferring any genetic let's say, modification for something really extreme. Like people say, okay, this is a genetic modified plant resistant to glyphosate. No, this is not the case of glyphosate. We are talking about natural compounds that usually they can be produced by a plant, okay? and also they can be released by another plant. So it's something completely different. You will see. Okay, so this is the controversial. You have the traditional one, the evaluation of crude extract and plant residues. Which natural products are responsible by activity? We don't know. Today, what are their mode of action is important, and what is even more important, what is their fate, toxicity and role in the ecosystem? Because if we want to use one compound rather than the other one, you must be sure about how safe and how is the real mode of action of the first one, okay? Important, as I mentioned, when I change the philosophy of this kind of work, you must think about three different main and important things. One is the selection of the starting material. Now the selection is not because some people is telling you, okay, this is for headache. No, doesn't work, okay? So now it's an observation in the field. Sometimes the observation in the field is because the agriculture, the farmers can tell you, okay, I saw this, I use this, and you must make a translation of the whole information and try to see what is really important and what is really just, let's say, coincidence, okay? The second important thing is extraction methodology. Why? Because we want to mimic, in some way, we want to mimic what's happening in nature. So if we want to mimic what's happening in nature, obviously in nature at the moment, we have no dichloromethane, we have no methanol, we have no ethanol, just making direct extraction. We usually have water. And in the polluted air, when you have a very polluted air, you have some trace of acid, but not too much, okay? Otherwise we can survive. And the extraction methodology should be changed. And we must invite if you want, let's say, okay? And of course, something that is really important during the time, all the time, making evaluation of bioactivity. So rather to look for one typical kind of molecules, rather to look for one part of the plant, which would be flower, root, stem, or any other part, we must to look for the bioactivity of those components. So the first question is dry plant or fresh plant? A live plant or dead plant? So you must to consider many options. And of course it's not easy, because when you, for sure, when you talk about organic chemist, I'm organic chemist, and you say, okay, you must to handle water extract, say, what? No, forget it. Because we are thinking about, oh, this is very difficult for me, you know. They provide a very source for infestation. The microorganisms can also the enzymes can make their own job and so on, and can be destroyed. Almost the whole thing is destroyed. And we want to know exactly what's happening in nature. So we must to prevent the system as it is. It is important. Well, in the case of extraction, rather than use massive extraction using the organic solvent to obtain the maximum amount of compounds, we are making collection of lixiviates from roots or aerial parts. And we make collection of root exudate. Now on, we are also introducing some system that help a lot, which is the CO2 in supercritical conditions, so supercritical solvent. And the use of CO2 is very helpful, as I mentioned, because you can have, you can have a very good collection here. It is important to know that you have the extractor, okay, and you put here the plant. The gas is going through this way. It's not a gas, it's a liquid, okay? It's under pressure, liquid pressure, okay? Pass through the extractor, going here, and then you have cyclonic separator that can be by the pressure, you can obtain the clean extract without any solvent. This is very nice system. Okay, if we are thinking about nature, we invented this system, pluviotron. Pluviotron is a chamber here where you can put any kind of plant that you want, any part of the plant that you want. A live plant, dry plant, any kind, okay? And then here, what you mimic is what kind of rain do you want? Yes, soft rain, intensive rain, or what kind of rain do you want, okay? And you say, okay, well, I put the water here and then collect it, okay, here, and I have a recycle pump to put again the water on top. But I have here in the recycle collector, in the recirculate collector here, we have also collecting resin, interchange resin, to take all the organic molecules that comes with the extract, and the water comes to the top, okay? If you want to make a special exudation, we use another system we call Sirex, okay? And you have perlite glass here to avoid any retention interaction with the system. Then you have this, again, the recycle system here, and this is the amberlite. Amberlite is amberlite XAD7 that contain here, and also the water comes to the top. So in this amberlite, then you take it, pass organic solvent, and then you have a collection of molecules that you can obtain directly from the exudate. Okay, this is a small one, but you can upgrade until, let's say, 100 meters, square meters. So any kind, just put your imagination, okay? Okay, important, very important. We are crazy because we want to have amount and purity of our compounds to check the bioactivity, okay? Don't forget, when you are testing for bioactive compounds, a little impurity, a little influence of a secondary compounds could make a wrong answer in the bioassay, okay? So we look for amount and purity. The amount sometimes you get from crystallization, normal one, or by distillation, and the purity you must to check by chromatography, and of course by GZMS and so on. So you make analysis and semi-preparative to make an isolation. Now we have very nice equipment for HPLC. So you have flash chromatography first for large amount, then semi-prep, and then you make a, let's say, a protocol to make a correct isolation. And sometimes you say, okay, collect from the starting point that the line is growing up. Here in the second one, just stop it and change for the second one. So you can make a, they have, the machine can calculate exactly the shoulder and when they must to change based on the absorption. Could be UV detector, diode ray, or could be a reflection index, because reflection index is more powerful for us. Usually we have no UV absorption, okay? So it's difficult. The problem, when you are working with refraction index, what happens? You have no gradient. It should be constant, 30%, 20%, 10%. So firstly, you must to make a good selection in the protocol, okay? And then you go through the TLC, paper, silica, RP, and so on, column chromatography, semi-prep, but at the end, we have also a big battery of different kind of columns. So you can have GC, HPLC, and so on to be sure that the molecules that you have are really pure. And finally, what do you go? You go through tandem techniques, evenated techniques, with UV, MS, NMR, and metabolomic studies. So we know, because we have the technology, but 20 years ago, it doesn't work. So you can imagine how fast it's changing. And with the II, we have thousands and thousands of new possibilities that we can use for the near future, actually for the present. Okay, let me just show you something. We have this equipment, but now we are changing again. This equipment is very nice because you have an HPLC, you have an NMR, and you have the MS connected. Everything is connected. So you are detected with the UV, the diode ray detector. You detect what peak are you, okay? And you say, okay, because the UV, I stop stop the chromatography. And I send 95% to the NMR and 0.5 to MS, okay? And what I'm doing is, I run the MS here, and I run the NMR in this window. So I will show you. Here is how it looks. So you have a mixture, and you have, on real time, you have in BOA in 8 minutes, BOA in 7.1, and DBOA. And then you have here, you can run mono and bidimensional NMR. So you have the possibility to have COSI, you have no echo, because now we are working with HMQC, HMBC, as you know, because inverse detection is more sensitive and they give you more information, okay? But only in one point. So you stop it, send it, and do it. Okay. This is how it looks. You can see the molecule and some of the degradation product here. This is the peak and the UV. The carbon-13 also, you have the molecule here. Of course, you make a different kind of techniques for avoid the solvent, the signal, okay? And we are using here THF and also water, deuterated waters to make the HPLC. Okay, you have very nice techniques working on NMR analysis, like a DOSE-1D. This is one of my favorite, because in the DOSE-1D, we can see how are connected the protons of a sugar in a big molecule, a complex molecule, starting from one single signal, a numeric signal of the sugar, and then you can pop, making irradiation of the whole system, and you can see which is which. This is really important. So you have here several ones, and what you do is, this is the normal NMR, okay? Presaturation signal, so you avoid the signal of the solvent, and then you have the DOSE-1D, as you can see here, all the signals of the molecule. Okay, I'm working since 78 with a 60 megahertz, 60 megahertz. Little machine, continuous magnet, but what's what I have by the time.
We have 1 year.
Yeah.
I'll show you later.
Okay, so you know what I mean with this. So you can see only some peculiar, let's say, distinguished proton, like olefinic protons, proton connected with a carbon with a contain OH, double bond, and so on, but not so many. Everyone is absolutely complete, collapsed. Then I was working in Louisiana State University in Baton Rouge, and I had, by that time, was in 87, then I'd been 89, 91, 93, 95, every year there. I was associate professor there. It was very nice because as soon as I arrived, I have 100 for me, 100 to do my work. 100, 60, 100, okay. With Fourier transform, big advantage, okay. Second, I have a 200 for routine, 200 megahertz. So what I do by the time was just running carbon-13 in the 200 megahertz, enough. And a new, wonderful 400. 400 megahertz by the time, 87, it's like a fly, you know, I was flying in the sky. Because I can see how the signal were all overlapped, and then was very clean. And I can see one by one. This is made in a 400. Now we have 600, actually I forgot. I have 6, but we change for another 5 because we increase the other one, 700. So we have 700, 500, 400. 400 for routine. How changing everything. And 700, sometime we do the NMR structural elucidation with less than 1 milligram. 0.3, 0.4 could be enough. 700. 2025, okay. Okay, as I mentioned, this is one of the molecules. I really love it. Those are very complex. You have saponins. I will show you saponins during the day. Very nice talk. In this case, you have compound 1 and 2, and with the DOSE, you have very clear signals here. So you can see very clear. So in the case of the sugar, that are many concentrated over this position, you can have one of the anomeric proton and try to make irradiation, precise irradiation with DOSE 1D, and you can see how it's clean and how you can distinguish. And in the molecular, you have here how the methyl groups could be assigned to the molecule, and of course, that's what I mentioned. You have here several ones that are really very important text signals in this portion, and we'll see how it looks. Very nice looks. This is agabritocyte B and agabritocyte Z, and with the toxic 1D, you can see the sugar, okay? Sugar connected. And you say, okay, without destroy the molecule, don't forget, because we want to use the molecule for bioassay, okay? So we don't want to destroy any molecule, any milligram. It's very, very valuable molecule, okay? You must to take and to assign in ambiguously proton by proton, okay? So with this technique, you can have with the toxic 1D, you have a garlic, you have a xylyl, you have a glucose, you have everyone, just taking advantage of the anomeric proton and then give you only the one that are connected in the same system of each molecule. Okay, this is an appetizer, so don't worry, you will see something else. That's the general structure, that's the general methodology. Selection of plants. We do the selection of plants based on a problem and based normally, usually on bioassays. It is much better to expend some time, also money, because it's money obviously, and your time because you are working for the PhD or whatever, or for a postdoc position. You must to make a selection of the plant. What plant I want to use? What plant I want to study? Maybe you say, Francisco, I'm very, very interested on invasive plant, and you show me what is the problem, okay? I try to make an analysis of the problem and try to see what is much better, what kind of interaction we must to check. But anyway, we choose two different relative easy bioassay. The first one is coleoptile. We choose the wheat coleoptile bioassay. I will see in a moment. And the second one is the seed bioassay. We choose the seeds of the plants where we want to check what is the influence that produce my plant, okay? My target plant. This is the target, and this is the plant that I want to make a selection. As soon as I convince that the right one is this, I start my work. Okay. What kind of extract? Again, dry, fresh, alive, dye, root exudate, everyone. I must to check everyone. Produce small extracts and run bioassays. Based on the bioassays, I will say, okay, this, or I say this. I will choose what is the best way for extraction based on the bioactivity, not based on how nice it is or how easy it is to do the bioassay, okay? Of course, then, you are chemists, you are biochemists or whatever, you are familiar with the fractionation. So we go through fractionation. Based on what? Based usually on HPLC, flash chromatography, semi-prep, sometimes semi-prep TLC, we use CAMAC, we can use any other technique that can be automatically running or just doing by yourself and then scratching all the line and then re-extract it, okay? So at the end, you can imagine that you have pure compounds, but you must convince me which compound do you have and what is the purity of the compound that you have. So you must run the whole set of bioassays, and don't forget something, because the people sometimes are confusing with characterization and elucidation, and sometimes it's confusing with identification. When I can identify? When I have reference. For instance, if I'm looking for laryngenin, I have laryngenin, so I just check my compound based on the MES, based on NMR, and based on many other GCMS or whatever, and I say, okay, I can compare, and the fingerprints tell me that this is laryngenin, okay. But what happens if it's not laryngenin, it's something else? So you must run whole set of things, means IR, NMR, MS, and so on, and try to convince what kind of structure is the one that you have, okay? In that case, to prepare the puzzle, you have a structural elucidation, and you must to characterize the compound. And it's something that I want to keep in your mind after a couple of minutes, as I mentioned, with this, okay, old traditional way is to look for one particular family of compounds based on the family relationship. For instance, I know that Asteraceae usually contain sesquiterpilactone. I know that Centaurea in general contain sesquiterpilactone. So I was looking for sesquiterpilactone. That's my goal by that time, okay? But now no. You really don't know exactly what is at the end, because you are looking on the structure of the compound that shows the best activity. And this is the important change, you know. What do you mean with this? So what I mean with this, very simple. You must go with an open eyes and see maybe a triterpene, maybe it's a diterpene, maybe it's a phenolic, maybe it's, you don't know. So please go ahead and try to explain me which is the real compound that is involved in the bioactivity. Okay, what kind of bioassay I mentioned that we run? We run two. One is the coleoptile bioassay, I will show you in a minute, and phytotoxicity bioassay with STS, standard target species. It is a collection of monocots and dicots, and we're running to check if it's working or not in the standard. Then we go through the real life and try to check with the problem that we are facing in the field, okay? Then, as soon as I know, okay, this is my problem with bioassay, so this is kind of which are the problematic in my case. So previously I had to optimize the bioassay and try to check what is the bioassay toxicity for those compounds, for those species. Of course, in life you have photoperiods, so you must to take in account also the photoperiods. So in the growth chamber, organized by 12 hours, light, no light, and so on, and try to see what is the influence, and to look for the mode of action. Okay, and then of course you must to go through the field and greenhouse. Greenhouse is okay. It's giving you an idea about what is the evolution, how it looks, and so on. But don't forget, the real test is the field. Because if it's working in the field, wonderful. If it's in the greenhouse, potential. Okay, it's not the same. To be potential that you have really active action. Okay, this is how it looks, the weak coleoptile bioassay. The weak coleoptile bioassay, we cut it, this one, with this guillotine, we cut it 5 millimeters with coleoptile. Why etiolated coleoptile? Because we want to avoid any kind of interference with photosynthesis. So we don't need chlorophyll in any way, okay? Just want to see how is growing up the cells. At this point, we check coleoptile elongation and cell growth, okay? And this is how it looks. And indeed, you can see here sometime this very growth in the different size. But we're talking about 5 millimeters. If you have my eyes, please forget it. The number of mistakes that you can measure could be bigger than you can imagine. So we invited also a new equipment, and the equipment is calling that the one that we call photomet. With the photomet, you put the replicas in one square, in one frame, and you put the 5, and take a picture. When you take a picture, the algorithm is making a calculation about how is the elongation and give you a value, okay? And you can compare your treatment with the control. Every time we compare treatment with control, positive control, okay? And when we have at the end is graphics. Where are graphics? What kind of graphics? We have a graphics that explain you if it's 0, it's equal to control. If it's negative, inhibition. If it's positive, stimulation. So that's the way, very easy to interpret, okay? But very, very tedious if you must to make a calculation one by one. It's very difficult because you are talking about 3,000 measures, 5,000, and you can, at the end, you have no eyes. You have a very, very crazy mind, okay? Okay, so we start here, store in the growth chamber, and we took the picture of this. This takes two advantages. One is that you make let's say, homogenate mistakes. You can calculate it, and you can calibrate time by time. But also you have a very good data sheet, data information, so you have database. Okay, so maybe next year you have a new algorithm that can calculate something else. For instance, the way that is making a curve, because sometimes it's not straight. It's making a curve, so it can be related with some physiology effects. So it's something really important to have this information storage. Okay, the sulfur, we are using a buffer solution with citric, and I will move this way because I feel so uncomfortable here. Okay. Sorry. Much better. So you have a buffer solution here. Is the citric, monohydrate, potassium phosphate, and then sucrose, and pH adjusted to 5.6. Okay, and the positive control that we are using is terbutrin and trisulfuron in this ratio that usually is normally called logram, but you can use any other that you want to be sure. This is the result of one of bioassays that we ran several years ago to standardize the system. Okay, the second bioassay. The second bioassay is the seed bioassay. So in that case, it depends on the standard Thayer species that you want. You have Lepidium sativum, cress, Lactuca sativa, lettuce, Lycopersicum esculentum, tomato, and also monocots, allium cepa, onion, so you have a good salad, okay? You can see how it looks and how is the influence in monocots and dicots. So this is giving you an idea about what is important. We measure 3 parameters. Germination, of course, how many seeds are germinated. Second one, we measure how is the elongation of the root length and the shoot length. Because of what? Because if the root is very short, this plant can survive because they have no options to uptake the nutrients, okay? But also the other way around, if you have a very nice root system, but you have a very, very little shoot, you have no possibilities to catch the light from the aerial part, so you have the photosynthesis not working with you and many of the effects, so you can survive also. So you have these 3 possibilities: stop germination, modify roots, or modify the shoots. Okay, again, it's very nice. At the beginning, I remember many of my students and myself just working, putting the seed in the center, shoot for one side, root for another side, and try to measure with a rule and say, okay, 4.5. 4.5, maybe it's 4.6. Well, I don't know exactly. So please, come to see, 4.3, oh my God. So what is an average? Unbelievable. We must avoid this, okay? No, not anymore, not anymore. So we invented also, and we have a patent for this, phytomet. And the phytomet you put in the middle of the line, you put the seeds. Root, shoot, and then with the electronic pencil, you make pap, 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 you measure. Pap, 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 you mark. And they give you automatically the distance, the roots, and so on. And if you have no roots or shoot for one single thing, it's because the germination was not successful, okay? Again, it depends on what? It depends on the size of the seeds. It depends on the number of seeds you must to put in the petri dishes. It depends on many factors that you must to optimize, okay? And this is how it looks. Those graphics, you will see many during the day. So everything 0, what is the meaning? Equal to control. Nothing really important. Everything down, even if I can see the number exactly, 47, 85, no, inhibition, doesn't matter, okay? We will see how big is the inhibition or not. And of course, everything up here, stimulation. And sometimes you see something that is very, very, let's say, frequent. When you are testing in bioassays, you can see sometimes a strong inhibition, but then turn to stimulation. Inhibition, stimulation, depending on the concentration. Means that you are affecting different kind of enzymes, and sometimes it's provoking one effect, but not under certain concentration. You remember Paracelso? They say the difference between a venom and a drug is the doses. It's almost the same. It depends on the doses, okay? Okay, so we collect phototoxicity, we have this, and then we say, okay, great. I have 30,000 data. What I can do? So, no problem. I start with this collection and I say, have you taken in consideration this? No. I can take this? No. You must to be sure that you are really objective in your choice, and the data is accurate data, and is not something that you are going with pre-consideration of how is the effect that you expect. Okay, the effect is the effect, and your problem is to make an interpretation, right? So we do this kind of analysis, cluster analysis, and this cluster analysis this is the positive control, and then you have a gradient of points here, and as closer are you as Lagrange, for instance, in this case, stronger are you. It's a stronger power. Okay. So, for instance, P8 or P6, I'm sorry, P6 is not so big, but P1 is one of the best. So it's something really objective. So you don't need to take care about the mistakes, and can compare at the same time simultaneously many multivariants. Okay, it is important. All right, so this is time to show you something. This is methodology, this is how it looks, this is how it works, and now let me show you some of the examples. I selected several ones because we have a large collection in this case. Let's start with Allelopathic studies on wild plants. Maybe you know some of those. Some of those plants are really beautiful plants, like Cinara cardunculus, Urucloa rusinensis, Rapanea umbellata, and some others. And some others, maybe you say, okay, no, but you can imagine something. You can imagine something. For instance, let's say Cinara cardunculus. Cinara cardunculus, I will show you two things. One, this one, and then a little later, okay? Cinara cardunculus, oh, great. Asteracea, sesquiterpilactum, wonderful. So I have agarine, Cinaropicrin, groschemin, and then 11-13 dihydroxy 8 desoxygroschemin. Listen, active, 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 non-active. Ha! Non-active. And you say, well, what is the main difference between this collection and this? The main difference comes for the position 11-13. The position 11-13, in this case, is an alpha-beta unsaturated system, so you have a Michael acceptor, Michael addition acceptor here. So all nucleophilic reaction can be in this point. Also you have a second one here in the side chain. The same here, and here only one. Okay, but here you have no one. You have OH, 11 and 7, 13 and 7. I'm sorry, I'm 11. So you have dihydroxy. So this is something that you can imagine. You say, okay, usually happens. In nature, when you have a bioactive molecule, usually it's because you have at least two linkage of the proteins or the enzyme to the molecule. And this is very, very much related with the possibilities to have a Michael addition. And this is a very nice plant. It's a perennial, it's still native of Mediterranean region, but has invaded America areas where native plants community propagate and degrade. We'll see, because I say active. Active against what? So tell me against what, okay? Various biological activity has been done, antioxidant, cytotoxic, antimicrobial, and I added another one, which is also anti-colon activity, anti-colon cancer activity. So it's very, very nice, very nice. What's happening is, okay, I have four molecules. Maybe is the component is the activity of the show, the activities belonging to one single compound or the cocktail. And the cocktail in what ratio it should be. So in that case, we choose the possibility to study the combination of the different sesquiterpilactone and try to see how it is active and what kind of activity. This is the one that we call it, is called isobolograms. The isobolograms here, you have here, and you have your point here in a green part is additivity. Simple. 1 + 1, 2. That's it. Okay? But sometimes you have this square here. If the point is right here, it is antagonism. Means that you put the combination, and rather than get stimulation or whatever, you do the opposite one because it's stopped your activity, okay? But the more fascinating one and most interesting for us is the triangle. You have here triangle means synergism. Means the typical word that say 1 + 1 is more than 2. Because you have more activity than the one that you expected separately compounds, okay? Additivity is just the sum of the individual activities. Synergism is the one that we really like it. Is the mixture of compounds is greater than the sum of the individual activities, and of course antagonism. So when we choose this, we found that in different 17 binary mixtures, different composition, you put one stop, and then we change the second one, change the first one, second one, and so on. So you make a 17 binary mixtures. You have the active ingredients are this one, and the non-active is this one. Between the sesquiterpilactone binary mixture agarine B and grossemin, listen, active and active, you have here, okay? Means you have, in this case, synergistic effect. When you have non-active compound and active, non-active compound and active, you have the square and the triangle. So here only the square means that you have antagonism. Here you have a possibility based on the concentration to change a little bit, but when the concentration, as you see here, 70%, 75 or 25 change, completely antagonist. So they stop the activity of the compound. So from that study, you say that coleoptile bioassay provides an effective tool to evaluate the interaction between compounds. The minor combination of the study lactone show you what is the synergistic, what is the agonism, what is the antagonism, and what is the sum. And the activity of the extract cannot always be explained as the mere sum of activities. This is something that happens. If you are a student or you are the mentor of the student, and your student comes to you with the results and say, okay, listen, professor, this is the extract, original extract. Oh, great activity. Fractions. Oh, great. Pure compounds. And say, what's happened with activity? Almost disappear. Almost disappear. Why? Because in nature, nothing is like it seems. In nature, it's a combination. And in the original extract, everything was together. So you have the synergistic effect easily to convince and to produce it. But when you bring it a lot, alone, you have two problems. First is alone. Alone is alone. For good things and for bad things, okay? And when you are not in the mixture, the solubility is changing dramatically. Sometimes when you go to the final compounds, it's not solving anymore in water. Maybe in dimethol, maybe in methanol, but not in water. So, how you explain? That's your problem, that's your target, that's your job, okay? To explain what happened and what you find. Don't forget, if you ask the wrong question, if the bioassay is not good, well designed, the answer is wrong, okay? So please, invest all the time you need it to set up a good bioassay. This is really important, okay? Urocloa russicensis. Do you know this plant? No? Oh my God. Many pastures in Brazil are mainly composed of Urocloa species. The farmers observe problems in the reduction of the production in soybean. That's the question. Soybean. When the crop is sown after the drying of the pasture of Urocloa with the glyphosate herbicide. So you say, okay, I use it glyphosate, but then when the plant is dry, I got problems. Why? Because the glyphosate is working very well. So, firstly, we try to corroborate the glyphosate, the desiccation with ursensis. Glyphosate is the growth and productivity generally modified. Try to look for the isolation identification of the compounds. Make an evaluation of the compounds on soy and see what happened. Simple. The allelopathic behavior has related with 3 different orthocumaric acid, Cumaric cis and trans, and aconitic acid. They're here, and here. So it was not so complicated structure. You have detail here. After 5 days of glyphosate application, A. B. 10 days after application of glyphosate. Oh, control. C. Untreated. Very healthy. Okay, wonderful. So how we can explain? Because the major compound was not the acetic acid. Well, no, was this one, protodiostin. It is a saponin. So, but it's a desmonic saponin. You have sugar here, but also here. So, majority compound isolate from the fraction extract with after with and without glyphosate treatment was this compound. So you have here control, protocol 32, 80, 120, 240 micrograms, and you increase the concentration of this particular compound. And you can see here how was the inhibition. Okay, is the dry weight or roots was strongly inhibited, almost 75%. When the glyphosate also make a stimulation in this case. So it is very nice because you are thinking about the most really obvious, let's say, these single molecules, but then the real one are not this one, it's this one. Okay? So the isolated main compound is protodiostin, is phytotoxic for soybean seedlings. This is the one that is making the really inhibition of soybeans. Okay? Protodiostin could be responsible for the reduction observed of soybeans planted after desiccation of glyphosate. So it's not a question that the plant is this and the glyphosate is this, is the consequence. The consequence is this molecule, it should be the biggest one and the strongest one. Okay, Bidden sulfurea. Listen. In the Franca region of Brazil. Very nice, beautiful plant. I don't like to say wheat is a bad plant. It's not a bad plant. Plants are never a bad. The problem is because they are growing up and in the place and the time that we really don't need it. Okay? This is also ornamental. Listen the sentence. Onde había plant margaridinha or camping colonial now desenvolvia. I don't know my pronunciation, excuse me. I just tried. But it's something that happens. I mean, the farmer show us and say, hey, if you can see here, this plant doesn't work. Oh, it's working, okay? So Bidden sulfurea was able to eliminate Panicum maximum wheat that infects coffee plantation without affecting the crop. Coffee plantation, Minas Gerais, Lavras, many places, coffee plantation. Here, what I can tell you about coffee plantations? You are the king in country in the production. This fact could occur due to allelopathic phenomenon. We don't know. Maybe Bidden sulfurea affecting Panicum maximum. So listen, the crop is coffee, okay? But this is the fate, the fair between one wheat against another wheat. Between both are fighting. I tell you, Bidden sulfurea is an herbaceous plant belonging to a family Asteraceae, originally from North America and introduced in Brazil as ornamental and very wide distribution. You maybe, I think that you go through the field because the really meaning of wide and big is Brazil. No discussion. When we are talking about Amendoim plantation, bigger. Coffee, it's so big. So for sure you will see this plant in some way. It is a vigorous plant that tolerates drought after germination and most insect attacks. Important, insect attacks. Bioguided isolation. So let's go. We took leaves separately, leaves, roots, and we prepare the system and try to see, hey, you can see this is almost a crop. Unbelievable. Okay, what we found is the isolation from the leaves are
sesquiterpene, in this case, germacanolides. This one is costunolide. It's one of the most simple costunolide. It's a trans germacanolide. Okay. Then you have eudesmanolide like this, and in a very high proportion, you have 77 milligrams, 71, 67. So it's a big number. Then some collection of diterpenes, some fatty acids, and then also some triterpenes. If we check the bioactivities, you see the positive control, but you have here number 1, costunolide. You see, you have also a profile of activity better than Logran, because it's remain active also with dilution. Here we are talking about 10 microgram, 10 to the minus 6 milligram. It's unbelievable. It's really very active. Rainosins and tamarin were isolated from the 3 fractions, and we tested. Okay, we tested also against Amaranthus videns and Panicum maximum, the one that was really active. And of course, they took advantage in the germination, also in the root length and the shoot length, the same than Amaranthus viridens. So, in this case, we can say that really they are the main isolated compounds, costunolide, on the same species and the original extract. And the result of the study on the root extract, listen, aerial part, roots. No significant phytotoxicity was observed on the seeds. The isolation of the root extract gave 9 compounds other than those isolated from the leaves. We use also bioassays in hydroponic conditions. Just try to mimic hydroponic condition, greenhouse, and then go to the field. Okay? Why hydroponic? Because you can control many factors in the bioassay. That's the main reason. That's no other. So you have here the control. You have 1, 2, and 3. 1, 2, 3. 1, 2, 3. And you can see also how was the combination for this Amaranthus viridis. I want to point it out. Also the concentration, 10 micromolar. Okay. In the case of Santamarin, and using Panicum maximum, which was one of the weeds more effective compound, is especially strong and inhibited. You see? Santamarin. Okay, so in this case you have a combination of 3 sesquiterpene. The 3 lactone are biosynthesized in large quantities, and they can directly involve in the inhibitory behavior of this plant described in Brazilian farmers. So we have an explanation. We can say whatever you say is because of this, is the combination. Okay, Annona glabra. You know this plant? Yes, sure. No? Oh my God. Oh my God. This tree is native from Florida, in the United States, the Caribbean, Central and South America, and West Africa. Glabra grows in swamps, some swamps intolerant in salt water and cannot grow on dry soils. It is known that the fruit is very nice as anti-cancer, anti-mutagenic, antioxidant. So you have this plant here, the fruit, and we say, okay, let's try to make a optimization of the extract. Okay, so we can use almost the same kind of solvent, but using different techniques. In this case, we use ultrasound extraction to obtain the most active extract. Isolate the compound and try to see the evaluation. This is the design of experiment, the extraction with ultrasound, and we use acetone, methanol, this combination, and try to see what is much better, because we know in this case what kind of compound we are looking for. Okay? When you know what kind of compound you're looking for, and you know the part of the plant where they are located, they are produced, it's very easy. If I say, okay, I'm going to Sao Carlos, and I want to catch money, where I'm going? To the bank, first option, or to the cash machine. Okay? I don't go to a tavern or a coffee shop or something like that, because usually the money is not there. Okay? So this is the same. If I know what kind of compound and I know what kind of place or the plant is the one that I want to extract, we can optimize. The condition in this case was very nice. You have temperature 5 degrees, 25 milliliters, time 5 minutes. 5 minutes. The proof thin, and then the salt acetone, in this case, power 50 and cycle of 0.5. So you have a very nice here combination. Then, of course, we must to check what happened, and you have a combination of diterpenes, esteroids, and acetogenin. Acetogenin are belonging to fatty acids, the same pathway, okay? Acetogenic. Very, very important against pancreas cancer and also colon cancer. And you know the pancreas is very difficult to find options in this way. Acetogenin. Also, we have a very nice job doing with another family of compounds related with this. With this is a very nice fruit here in Guanábana. Guanábana. What? La guanábana, chirimoya, pero chirimoya gigante. Guanábana is a big, big one. What? What? Yaca. Yeah. Graviola, correct. Graviola. Wonderful. We choose in this case, I don't want to present it today, but it's something that was very related with acetogenin because it's very rich in acetogenins. So you can prepare a tea, not with the fruit, with the leaves of the tree. Prepare a tea and drink it, and you can be that your pancreas and also your colon could be prevented against this kind of cancer. So I strongly recommend it. Okay, let's continue. So we have the design of experiment using activity make possible to make the isolation in large amount of this compound, particularly this compound. Agave. Okay, agave. I call it non-manipulated ecosystem, but indeed you have that depending on the country is a cultivate plant. For instance, in Mexico. In Mexico, you have many kind of agaves, but they have many things, as you know. Why? Because they can produce many things, okay? You know, something like something sweet, like we can use as a biofuels, natural sweeteners. This is very, very useful now. The syrup of agave is very useful. Prebiotics, nutraceutics, source of fiber, food, beverage, okay. Tequila, mezcal, these kind of things, so you know already. And the agaves, they contain about 480 species, usually from tropical and subtropical regions, arid and semi-arid climates, and is important source of steroidal saponins. And that was the reason, because we study agave, okay? Let me go a little bit deeper here with agave. Okay, what kind of steroidal saponins? You have sapogenins, which is the aglycon, and you have the glycosidic chain. Okay. But you have two options. Could be monodesmonic saponins that have only one side chain, one sugar chain, or bidesmonic. So you have one here, another one here. So you have two side chains at the same time. But listen, this is complex with two sugars. Even with one, it's okay. It's complicated. Two sugars, a little more complicated. 1, 2, 3, a little more complicated. You will see what happened now. 1, 2, 3, 4, 5 is the case of tigonenin with properties as antifungic. Tigogenic, aglycon is non-active. The only active is the one that is here. They have a problem with because it's amphoteric. So we try to dry, grow, soak, make a hydrocolloid extract, and try to see from the polar fraction, from the real polar fraction, we found here 7 fraction, and we make isolation and see what happened in the bioactivity. You can see here bioactivity fraction 6, 5, 4, and 3 are the best. So we try to see what we can find there, and we found 13 different saponins from agave or follana. You have here one, those are the components that they have, and they have also furostanic with sugar here, and they have only with these, with more than 5 and so on. So you have, those are the different side chains. When I say R, it's not an R. It is 1, 2, 3, 4, 1, 2, 3, 4, 5, and so on. So please think about the complexity of the structural oxidation. You must to discover which is which, silosa, fructose, glucose, and so on. Secondly, which is the connected point, okay? And what is the order, the sequence? This is connected with this is connected with this is connected with this, and so. And in addition, you must not cut it. Because originally what we do was just make a enzymatic hydrolyzation. So you make hydrolysis, then you cut the sugar, and then you try to analyze separately everyone, okay? But you don't need it. I mean, you don't like it. You want to have at the end the molecule in your hands to test it, okay? So, this is the system I mentioned. This was with a 500, and we use proton, carbon, DOC, toxi, ROC, toxi 2D, ROC 2D, HSQC, HMBC, HNQC, toxi. And now I will show you something else, a little more complicated. Okay, those are the bioactivity that show that these are very promising compounds, you see, control, and flucloxetine, 333 micromolar. Well, you see that you have some of the steroidal saponin. You have with it, when you have OH here and carbonyl here, it depends. You have phytotoxicity of 20. We tested 28 steroidal saponins, and we say that when you have no oxygenation here in its position, 12, it's active but not too much. When you have here COH, you have 280, 82, 88, but the best one are when you have a carbonyl here in 12 or hydroxy group in 12. Okay, flucloxetine, Soxhlet, maceration, vacuum chromatography, column chromatography, PLC. We purify. They are amphipathic nature. The presence of a structural relative form, similar polarity. So you have one sugar, you have one saponin, another saponin that differ on the orientation of one single oxygen. So how you can distinguish? Complicated. The isolation remains a considerable challenge, but we try. So you originally, as I mentioned, you do the methyl point, elemental analysis, redox, then total hydrolysis, methyl point, and so. Most common technique for, let's say, known compounds now, and NMR techniques, okay. So what we're doing now, to be able to identify saponin in a mixture without the need of isolate pure compounds, it is possible? Is possible or no? Yeah. We don't know. Yes, we'll see, yes. We have mixtures of 5 to 23 different saponins. Complicated. You must to identify each one, and to characterize the one that is unknown, okay? And you must to measure the ratio. I mean, in what proportion do you have in the mixture, okay? Because it is became very popular to have phytomedicine. You go to the farmer and you have parapharmaceutics, and you go to parapharmaceutics and say, please give me a plant that could be very healthy for my stomach. So, oh, well, no problem. This extra. Yeah? It's containing alcachofi. Good. Cinnaris collimus, by the way. Say, oh, okay, Cinnaris collimus. What kind of extra do you have? Sometimes you have no idea. What components are there? I have no idea. You know my size. You can make a calculation on how many milligrams I must to intake. And for instance, my friend Fatima can intake. I mean, obviously it's not the same ratio. She will take less than me, okay? But to do this, to make a good recipe for your problem, you must to know what is inside and in what proportion do you have, okay? So you can calculate, let's say, in terms of percentage. You say, the extract should be contain at least 10% of this plant. Okay. And this plant, at least 5% should contain fluorochronostatin. Okay. So you know how you will calculate or not? Without separation? It's a big challenge. We'll see. To optimize the extraction, it's another option, of course. Okay, I don't want to know kilograms and kilograms extracted with water, and then water methanol, and then try to re-extract it and to make some purification. It's going to be very tedious, and any process that we introduce in the company is increasing the price. And of course, to evaluate the biological activity of saponin-rich fractions, you must to be sure about what compounds do you have and in what amount. Otherwise, you can calculate what is the ratio. I mean, you say 10 micrograms of what? Of the total weight? No. We are thinking about single compounds, okay? Well, objectives, let's say. A spectroscopic data collection of the most representative aglycons. We say, okay, I know because we are working for many years in this project with agave, and we have a large collection of agave, a large collection of saponin from agave. Study the shielding variation produced by functional groups on the aglycon backbone. I know what is the aglycon, and based on the sugar, I can imagine what is connected directly to the aglycon, so the first linkage, and then I can try to calculate the other ones. We'll see. And the question is, I try to make an application of this method to a saponin-rich fraction. It is really important, because I want to know in a fraction what is there and which is which. Very difficult. That's the system that we design, is the HMII method. Is the HMBC method for aglycon identification. HMBC method for aglycon identification. So this method can show you what is the aglycon, and then you must to combine with the sugars, okay? So the method is based on our experience, of course, and the C finders where we found spirostanic, furostanic, and saponins in general. A total of 63 saponins and 30 aglycons was preparing at the first time. It was the first publication was in 21. Now it's more than double and increasing every day, because it's agave and also yucca. You can also increase the number. Okay, so listen to this. Steroidal type saponins. That's the way. And we try to characterize this one, exactly with this one, because we want to distinguish between the one that is closed and the one that is open. Okay? Spirostane against furostane backbone. We want to show also, we want to know exactly what is the chiral center C5 and C25. C25 and C5. Those are crucial. Okay. Then we want to check, I mentioned, remember, position 12, carbonyl OH, and the orientation should be better, the best. Okay. Alpha or beta here in 2. Alpha here or not, we'll see. Alpha, beta in 23, 24. So you have a functional groups, double bond, carbonyl, hydroxyl, and so. Okay, we know that the proton signaler methyl groups are very important. We have 21 here, 18, 19, also 27, and we can have a correlation between, by HMBC, between the proton and the carbon. So this is really important and the tricky question. Why? Because I listen the protons here, of the 21, and I have 1 bond, 2 bonds, 3 bonds. So I can connect the 21 with 22, and also with this one, and 27 with 25, 4 and 5 and 6, and make a cross assignment. It is very important because we can detect it with very precision. So let's go and see the influence. Proton carbon 13 chemical shift, ring F, depending of C25 configuration. So we choose many, as you can see here, and you see, okay, carbon 13 and proton. We look the position. Don't forget, we are listening a proton, a carbon, and HMBC, and HNQC, okay? And we look for this interaction, the carbon and the proton, and try to see what are the connection between 25, 26, and so on. So based on the carbon position, we say, okay, this is 31.6, 31.6, 31, 30, minus 5, minus 3, We can have some kind of correlation. Yes, we can have it. We have the option to have this methyl group here, H27, with this carbon in those two. Yes, we can. So we can make an arrangement, because we can also assign the chemical shape, the orientation, the configuration of the 25, R or S, based on the chemical shift. Okay? That's the table, big table. Okay, again, my eyes, so bad. So we try to follow, in a workflow, we try to follow the system in this way. Single signals. Try yes or not. Yes, this way. Yes or not. And you can go and follow the connection. The first one, you can see here and here. You see? You saw here and here. Second one, go to this way. I detected the second. Then the third, 4. And you can follow until the end. So you have until the end, you have an idea, exactly, precise idea about the structure that you have in your hands. Okay, it's complicated. Yes, it's complicated, but it's possible to do it in a mixture. Yes, we can. We try, in this case, we have bracteosa, identification of main saponins through HMBA methods, HPLC and NMR, and try to see what is the optimization. We optimize the extraction, because this not only, let's see, if I need to make a quick analysis, it should be very, very quick and efficient extraction. Okay, so we extracted with methanol water 822 saponin rich fraction here. In a set pack, you extract polymeric reverse phase cartridge, and then you go through HPLC and then to NMR. Okay, you have here how it looks. It is complex, yes, very complex. But don't be afraid, because we can look closer and we can distinguish which is which. Okay. So we have also the MS, high resolution MS, of course. MS, triple quadruple, okay? So you have an idea about what are the best fractionation that you have. It is very, very healthy, because helpful, because you can distinguish for each peak what are the peaks and what are the potential structure that we must to identify. So first screening, for instance, you say, okay, I will look for this region, you see, the methyl groups. Then I obtain multiplicity and also the carbon 13 here, here. I have here the first screening. You have the HMBC, you have the correlation, proton with the carbons, so you have the proton and the carbons, and then goes to the flow card. You follow the card and you have one green and the blue one. So you have an assignation of the C18, C19 and the position 3 and 6 as a glucosate. And the other ones, you have the red one here and the green one here. So you have what structure is this and what is wrong and what is okay. What is okay for 21, 18 and 19, and what are the multiplicity and the connection. Of course, you have to be sure about the stereochemistry. And the stereochemistry comes from the noise effects, that you can see the two-dimensional noise effects and also the HMBC again. So you have the connection between 27, 25, 26, and the 26 with 22, 21 with 22. So you have a cross connection here. Okay, I show you a very clean picture, but at the beginning was very, very difficult, until you have an idea about what is the line that you must to follow. Okay, from this first screening you have an idea, and the compound is the 25S Cantala saponin 1. And Solanum ispidum was antifungal activity and non-natural remedy. So we'll see what we can do. Urostanic, this is the HMBC with the different correlation and so on. And the furostanic type of saponins here. Again, we saw the correlation in the case of the second peak. The first one was for this one. Now we're talking about this, okay? And the second one shows the new structure here. New structure. Let's go, first screening. We have a more complicated. It's a fraction with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 16, 17, 18, 19, plus the little ones. Complicated, right? Complicated. Well, no problem. No problem because it's a big problem. So when we have a big problem, it's no problem. It's a problem of everyone. So no problem at all. So we check the mass, and then we call the anomeric proton here, this section. And we try to see what happened in the sugar shade, the replication. And we found, based on the mass, we found glucose at C4, galactose at 3.3, and glucose at C26. So you have a connection here and here. So you have substructures, okay? Then we connected the other ones, the other interrelationships. So you can follow the line and try to see how it looks. So please keep in mind, you have a bracteose ellipse, extraction, fractionation, HPLC, MS, and then you have at least biggest 10 saponins. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Plus the other ones, don't forget. Those are the saponins. I mean, the aglycons you know already here, but then you have sugar for many different positions here, here, and connected. We don't destroy the molecule. Important. This dereplication system don't destroy the molecule. So we describe for the first time the 25S cantalisonide 1 and bracteofuranosidos A and H, and isolate from the Tribulus terrestris. Okay, we check against different proliferation cells, and we say in the HeLa 100 micromolar 24 hours, and it's working relatively well here and here. Well, the question for us was very easy. I mean, we must optimize the extraction, okay? So we optimize the extraction, reaching furostanic saponins, bracteosa. And then we use reflux, Soxhler, maceration, and so on. The best one, of course, is the supercritical fluid extraction. Again, among green extraction are the ones, but this one with ultrasound is a very, very efficient way for green. Only 3 references have reported extraction of steroidal saponin with green technology. Only 3 in the world. We make the isolation, the extraction. The extraction, we optimize the extraction, and we optimize the temperature, sample solvent, cycle setup, amplitude, ultrasound, and so on. And then you can see the ratio here, plus and less. So you have an extraction of saponins. That's the curve where you can see the distribution. And the optimal condition were 20 milliliters, 25% of ethanol, 34 degrees, pulse of 43.7, 20% of amplitude, and 10 minutes. Well, you have this, and you have with this ratio influence of the time of extraction, so you have all the optimization here, 20 milliliters. And finally, it is important to have repeatability of the intermediate precision, because you want to provide something to the industry that you say, if you do this in this way, this way, this way, this way, finally you have this. So it is possible with the standard deviation and so on, so you have here the protocol. Conclusion, important in this part. In this part you have the HMBC spectrum, which is important to do it. HMIA method could be also applied for other genera with saponin. We are using for, I tell you, for agave and yucca, but we are also improving for some other. And of course, now we are using AI. I mean, we are teaching an AI specifically to do this, let's say, comparison. Okay? The possibility of differentiation between isomers. It is important to differentiate between isomers. The dereplication strategy using UPLC, cutoff, MS, HMAIS, and NMR spectroscopy led to identification of furostanic, in this case of Bracteosa, the isolation of 10, but what is more so very, very important, we can calculate exactly which is which and what is the ratio that you have in the mixture. It is really important. So it is important for, is not degrade the chemical characterization, the detection of new molecules, hidden saponins, sometimes overlapped, and it was not possible to make separately. Quality control, as I mentioned, for phytomedicine is great, but also for farmers is great. And fast study and lower time of sample preparation. So we have a very nice system. Here we have also something else. I mentioned that one of the main interaction is plant-plant interaction, plant-microorganism interaction. And this is one of the microorganisms I was studying for this interaction. But in this case was in the opposite way. I mean, no plant microorganism, was microorganism against plant. What microorganism? In this case was penicillium species. What for penicillium species from New Zealand. Remember yesterday we mentioned New Zealand. Why? When we finish this, we can stop. We're going to just a couple of. We have for 3 or 4 days, so don't worry. Even for 1 year, if you want. So, why New Zealand? Because we want to use untouched system if we want. Penicillium is everywhere, many things, but this one comes from New Zealand. Was relatively alone system, okay, isolated system. And in this case, we catch brevions, new molecules, new and novel structures, brevions, A, B, F, G, Z, D, E, F, and so on. The brevions, they have, you see, control and treatment, you have different things, but this is also important. Brevions E, 100%. Brevions C, 80%. You can see how are the difference and how are the the similarities. You have many things. Actually, we do a very nice review, is in Chemical Review, is a publication, and you can see all the synthesis that has been done based on this kind of structures. I recommend it, it's very nice. Oh, by the way, it's here. Okay. Okay, we make the synthesis. The syntone was this one, D, 1 plus this. Then we have this corresponding 5. Then 5 go through 7, and from 7 we go through 10. The synthesis of brevions, as soon as you have the syntone D, you can have an expansion, or you can protect it, reduction, and then syntone D go through syntone Z, and from 50 go through 54. So if you combine both of them, you must to check in synthesis. It's important to us to make a synthesis, but it's important also to know what happened with the intermediate. Sometimes the intermediate is enough. You don't need to go until the end, okay, to have active compound. So you have decalines, phenanthrenes, expanded molecules, and you can see here how was almost stimulation, but listen, everything plus minus 20 is normal, let's say. Everything up or down 20 is something interesting, okay? So here you have inhibition, strong inhibition here in general, but you have also in the case for Lolium rigidum, you have that 28 plus minus 28, they give you a very nice number here. And in the case of the root length, cotanil and Logran are the positive control, and you have you have a very nice molecule here, making an approach that the expanded was the best in this case, against Echinocloa cruzgali. Echinocloa cruzgali is the main wheat in the rice crop, okay? Well, Allelopathic studies on cultivar plants. I will stop here, okay?
Okay. I think we look for for question now, and then we stop for Portuguese. Any question? No? Tem uma questão aqui, depois a gente passa para o chat. I have a question.
Okay, let's go.
I'm very curious about the lactones with a conjugated double bond with the carbonyl or carboxyl. In cancer, we know that you have a microaddition when you have amino acid, residue of the amino acid with a nucleophilic group, you can have a microaddition there. And the same when you have groups, nucleophilic groups in the DNA, and do a microaddition in this kind of lactone. This is the main effect of this kind of compounds. I'm very curious. In Alelopatia, do you have an idea what happened?
Oh yeah, yeah. I mean, the answer is very simple. I have no idea. Nah. I mean, it's something that we must study in deep detail, okay? But in general, it's the same principle. If we have some samples, I think later on I will explain something. If we know the interaction that, the mode of action, you know exactly what is the enzyme or the protein that is affected, we found that many times it's related directly with the presence of the alpha, beta, and saturate system. But usually 2 is better than 1. So the same molecule with 2 different possibilities, better than 1. And sometimes don't need to be alpha, beta, and saturate system, but should be, for instance, epoxide. So the epoxide can be opened and can be linkage. But 1 plus, one alpha, beta plus the epoxide, or 2 epoxide at the same time. That's very nice. Because as you know, the epoxide could be opened in invasive or acid condition. And depending on what is the media, you can open it in one way or the other one, and the final receptor could be different, could be quite different. But usually 2 linkage should be needed for the allelopathic activity. Yes.
Now I don't have a question, but later when you show us in our equipment, how can you do the same, split it to, so that you can have the or fraction or compound and send it to anyone? Because I discussed with my students, I couldn't convince. Maybe now you can convince. Later, Luis, you can speak Spanish very well, understand very well about our equipment. Okay, later we go there and maybe he can convince you.
I don't know.
Okay, you have a question. Outside, please.
Also, Fatima, she also here.
If we're looking some kind of herbicide, there are many factors that involve to search a specific molecule. So, what I need to think when I am looking for a molecule to use as herbicide, which factors I need to close my eyes and focus on this?
Well, I tell you, this is something that is also why, not this year, but the year before, was given the Nobel Prize in chemistry, because the AI. There are several bank of data for enzymes, okay? So before to do any kind of speculation, whatever, you can check in this database, okay, working on silico. So you make an approach and try to see, please, this is the structure I have, and check in this data bank what kind of enzyme could be affected, and they make a lot of correlation and say major one this, second this, third one this, and then you make a choice. Say make a 3 or 4, whatever. As soon as you make a selection, you can imagine, for instance, it is an enzyme that controls the penetration into the cell. Okay, so the barrier of the cell. Okay, so you can choose specific silico studies for your molecule affecting that enzyme. You do the analysis, you do the complex, the molecule analysis, and the dynamic. Because, you know, it's not a question to say, okay, linkage, that's it. No. It should be what is the half-life of the complex. If the complex is enough to be consistent, okay? So you can explain what are the mode of action, which is really the key point, the story. The story is not only the molecule. The story is not only because the water or because the exudation. No. The story is finally when you know what kind of mode of action, what is the effect at the molecular level that you really expected. And that's the way that we are doing. Usually you check before with the II, okay, an approach about this structure, many possibilities. And there is some time, I will tell you, sometime it's interesting because you are looking for herbicide, okay? But we found sometime that our molecule for herbicide doesn't work. And the molecule, the data bank say, no, but maybe for this particular action, say, I never saw in this, yes. We do the silico and was wonderful, and we do the bioassay, wonderful. So they focus our attention in that way, okay? It's not one by one. It should be, as soon as you know a molecule, and you expect one kind of activity, choose in the database, data bank.
There is a question.
Professor, I have a question from myself. What kind of column did you use for the MS analysis of the extract of blood? Wasn't reverse phase one?
Right, reverse phase. Because with these kind of molecules, normal phase doesn't work. For sesquiterpilactone is okay, but for saponins, reverse phase. Yeah. Is a UPLC, actually nano HPLC now. The column is less than 1 centimeter. Very, very small. Okay, and now we are implementing the system because we are not using MS triple quadruple. We're using TINTOF system with mobility ion. So it's more sensible, okay? And with the nano molecules, with the nano separation, go through the TINTOF. So every molecule has different mobility ion. Even two isomers can be different, okay? And arrive to the detector at the end in different times. So you can detect it, okay? And you can look for target molecule or for untarget molecule. If you look for target molecule, wonderful, because it can be detected part per billion in a mixture, okay, without separation. And you are looking for untarget molecule, even better, because you never know what happened at the end. So, wonderful.
More questions?
Okay.
Okay, can you stop now? Okay, you are stop for a coffee break, please.
Okay, thank you.
15 minutes, 20 minutes. It's the other side. Okay, let's go there. Vocês fecham só pra gente. Okay, please go ahead.
Okay. So first of all, thank you for your patience, to be very patient with me, because I'm very happy, as you know, you give me the opportunity to talk about allelopathy. It's my life, you know, it's my life. Well, as you can imagine, you have many things. Firstly, you must to have an idea, it's important, idea. Secondly, you must to find the methodology, important. Instruments, methodology, systematic protocols, and so on. Thirdly, you must to convince the people to give the money to you and your group, okay, to do the job. Because sometimes you say, okay, he's crazy. The plants are talking each other? He's talking with what? No. We'll see. And I show you many times how it's talking in different ways, okay? They're signalings in many different ways. With some consequences since the physiological point of view, and some consequences since the life point of view. Because sometimes, as I mentioned, in plants it is impossible to grow up because the mobility in a different place. If you are an insect, if you are a mammal, you can go and move and you come here and say, oh, I feel not comfortable. So bye-bye, Francisco, you move, okay? But if you are a plant and you have the opportunity to grow up here, you must stay there, and there are no options, okay? For positive and for negative actions. Okay, so firstly, I was talking about non-manipulated system, but also agave, which is in the bridge between non-manipulated and manipulated. Now, let's go to some examples of allelopathic studies on cultivated plants. I will talk something about, well, we're studying many, but the main one has been Elianthus agnus, Oryza sativa, Graminae, Tectona grandis, and of course parasitic weeds. Those are very nice examples, and every time you saw something here are projects that we are developing in some way. Could be a European project, could be a national project, world project, so it depends. It depends because they come from many places. Okay, Elianthus agnus. When I started in 1987 to make a decision to work intensively on allelopathy, I'll be back to Spain in 1988, and I decided, okay, let's start with a project on allelopathy. And we say, why not Elianthus? Elianthus, they have many reference in literature where you can see that it is a good candidate. We have a background in allelopathy activity, like a Cooper and Streth in 1931, that the observed was called distribution in fiery ring in the sunflower Elianthus rigidus. Wilson and Rice in 1968, they also observed the pattern of distribution in herbaceous species around the common sunflower plant Elianthus agnus. After the analysis of several factors, light, nutrients, conclude that the phenomenon was not due to competitive interaction, because indeed was some compounds going through the soil, taken from the target plant and uptake it. Well, with this in mind, this was our objective: study the sunflower leaves by isolating and evaluating the phytotoxicity activity of their compounds. But important, we must study part of the crop that will not affect it to the final production, okay? So in this case, what we do is taking leaves, randomized taking leaves from the different plants. By the way, she's from Jaboticaba. This one. You know the name? Yes? She was collecting with us. She is agricultural engineering, excellent people. She was working very hard with us. Mario, yes? So we take the plant, we study the plant in different steps. For instance, sunflower, when it was 10 centimeters tall, when it was half a meter, when they have flower, and then close to harvested. And we took leaves, only leaves, because we want to have this one in good condition. You see what is one of the species. The question is, what species is the cultivar? In Andalusia we have a strong tradition on cultivars. And we have every day, let's say every year, we have at least 2 or 3 different cultivars, new cultivars, that is introduced in the market. So they have a plot where they are making an evaluation about the quality of the product and also the quality and the amount of the yield, actually, the yield of the production. So I was talking with the people, talking with agriculture, talking with the national and regional government, and we decided to start with 10 different cultivars, and now on we are studying 400 different cultivars. 400 different cultivars, it's a lot, believe me, a lot. Particularly the people there say, the people that are belonging to natural product chemistry, okay? They say, Francisco, you are crazy. I say, what? Oh, some flowers, you can expect it only diterpenes, that's it. Don't look for nothing else, nothing new under the sun. Say, well, they are changing with the sun, so maybe I will find something new. I changed the methodology, as I mentioned, of the extraction and so on, only surface and so on, and you say, okay, what you have in the leaves, and you look in the back, okay, you look for trichomes. Those are the trichomes. One is like a finger, like you can see here, like a finger, with a little ball on top. Second is a ball. It's a ball, really, it's a ball here. And the third one is like a hair. So it's more functional. But the other one is very interesting because, you know, curiosity of the chemist. Why you don't take a needle and touch the ball deep in HPLC solvent and check in HPLC what is there? Just curiosity, okay? Okay, we do it. Oh my God. In the balls are sesquiterpene-lactones. Wonderful. Really wonderful. But even more interesting for us, here in the finger you have elianols and glandulones. Those are new and novel skeletons in sesquiterpene. Novel skeleton in sesquiterpene. Elianols and glandulones. So you have two options. One is, okay, let's go one by one under the magnifier, okay, take it, dip it, take it, dip it, with something, one option. As soon as you have many students, crazy, wonderful. But they can kill you, of course. So your life is in danger. Or the other thing is, okay, we can do something about the fast methodology for extraction. Okay, we do. We try to just dip it in water and then concentrate the water and then re-extract it with organic solvent. This is one option, okay? And the other option is to say, okay, just take the leaves, dip it in dichloromethane for, let's say, 5 minutes, take out, and try to see what happens. So, this is the real electron microscope image again. And you can see here something interesting. Here, you know, you can distinguish what is this? The stones, where they open and close for respiration or for photosynthesis to catch the CO2 and make a transformation to liberate the oxygen. So everything is under the leaves, okay? And very interesting. So you have glandulon B, glandulon C that also are surrounding the stones. And we found that also play a very important role there because they are making control about the stones. I'm sorry. Of course, if you look for the head, you can find diterpenes. But this was now our main goal, okay? It was leaves. Why leaves? Because we don't want to destroy the production. Why leaves? Because are residues, waste from the crop, okay? So actually when the harvest is coming, they cut the head, taking the heads, the seeds, okay? And then all the rest of the material, the aerial part, just cut it or maybe just fiber. That's it. So we took the leaves, we took the dry residues, soaked it in DMSO, as I mentioned, dry residues, soaked in methanol, or then you have a water extract, liquid-liquid partition with DCM, liquid-liquid partition with ethyl acetate. Okay, that's what we found. So it's something else, you know. Sesquiterpene-lactone, of course, as I mentioned, one of my favorite ones, you have not too complicated molecules. So guaianolides with not too much functional functions. You see here, annullite, annullite C, D, E, and so on, but not so many. Some eliangolite, elivipolite, which is also a germacanolite, but these cis, and also trans elivipolite, trans cis double bond, elivipolite, and so on. And they have also elivipolite here, more complicated with a very nice ring here, 5-member ring. Of course, also diners, very interested diners. But our attention comes because we found elianols A, B, as you can see, and N. So we have a lot. Believe me, this molecule was playing with me almost 1 year. Unbelievable. Was part of the PhD of Rosa. You can call her and say, Rosa, do you know something about elianol E? Elianol A? Unbelievable. Do it. You know, she came with me and she said, Francisco, that's the NMR. I saw the NMR. That's the pure compound. Mountains, mountains. Oh, hills, very hills. What is this? So, I was so worried. I bring the sample to state because in 87, I'm sorry, I was in state, but 89, I was not. So in Spain again with my 60, my playing machine, I can do nothing almost. So I took the sample and bring it again in 89 and check it to do a very nice analysis in NMR, in 400 megahertz NMR. And happened two things. First, during the time that was in the bench, crystallized. So, interesting, crystallized. So I took one of the plant or the crystals and bring it to my friend. My friend is Frank. Frank is in Louisiana State University. Frank Fronsek. You can check Frank Fronsek. Is more than 1,000 papers on an X-ray diffraction index. Unbelievable. It is a great people. He showed me how the X-ray analysis can help you. He published the first time that you have the absolute configuration of one molecule only based on the oxygen that was present in the molecule. Usually, we must take a bromine or any kind of molecule any kind of atoms that can give you a correct position of the atoms. He do it just with oxygen, and then a DNA and many other things that he do an excellent job. So I was playing with my friend and say, Franz, the first one that catch the structure will be the first author. He said, okay, no problem. So he was, making that, and I was still working with the 400 by the time. And the question was, okay, let's change the temperature. So I changed the temperature to a little bit up. So I increased the temperature, not too much because it was in chloroform, okay? A little bit up to 50 degrees, not too much. And was completely clear. 1, 2 signals. So the hill was split in two. Everyone was completely clear. So you have at least two what? Two conformers. That in the room temperature was in equilibrium. So the room temperature make a possibility to have both at the same time. So you have a promedio, the average between both. So you have only mountain hills and hills. When you go up with the temperature, you can see that splitting one and one was very stable. And when you go down, also you can see completely black. So based on this, we do the whole analysis. And I got the structural elucidation and got this. And I was by that time working with Klaus Fischer, in the lab of Klaus Fischer. And he said, Francisco, are you sure about the structure? I say, yes, I think so. Well, but it's a sesquiterpene. Say, yes, I know that this is a sesquiterpene. So you can see here, you have 6, but then you have 2, 1, 2, 3, 4, and the 2 methyls. And if you are taking care, you can see 3 isoprene units there, completely clear, 3 isoprene units. But it was new. So it was new and novel structure. So we have the, let's say, advantage to give the name of the structure, Elianol. Elian name is the name that we give it. And you can see many options. with construction, with 6, with 7, rearrangement. We found many of those. In research, what is research? To look whatever everyone is looking for, but to see only what you can see, and not only one can see it. It was in the flower, it was, in the plant, in the leaves. How many years has been studying sunflower? 100 years working on it. 100. You know, it's there. So we saw it. Okay. Not only this, we also isolate 8 apocarotenoids. Apocarotenoids are the ones that usually in a plant is taking care of the stomes, open it and close it. But we have also annoyonine A, B, C, and so on, that they are also taking care of this. Also, Elinor this one. But even more, 5 sesquiterpenes like this, open sesquiterpene, plus from these 3 with a furan ring in a spiral ring. Very nice. It's the Eliespiron A and the Eliespiron Z. We make a complete structural elucidation. Also, we have the X-ray for that molecule. And it is also a novel structure of sesquiterpene. So you have here an example, you can have brevions from New Zealand. Remember the microorganism penicillium was also another novel molecule. Another 2 structures, novel structures. And something else, of course, lignans. We have also Elianane, which is a chalcone and flavonoids. And how it looks in the bioassay, okay? You can see, as you can see here, 9, 13, and 19. 9, 13, and 19. They are very promising molecule because they are very active here, the lignans and the flavonoids. In the collected bioassay, in the case of sesquiterpelactone, you have a very nice collection here. You have 21 to 23, 9, 7, 22, where you have a collection. And as Fatima, as I mentioned before, you have here 1, 2, 1, 2, 3, 1, 2, 3, 1, 2, but this can be oxidized, so you can find something here, and also here 1 and 2 Michael addition acceptors. So they are very well related with allelopathic activities. At the moment, based on our results, during the last 30 years of allelopathic study on sunflower, 40 scientific publications on the isolation, structural elucidation, partial biosynthesis, biogenesis, total synthesis, and so on has been published. 2 new families of sesquiterpenoids, Eliananes and Eliespirane. 43 syntheses of members of Eliananes family has been inspired all around the world, including our work. It was also, at the beginning, very frustration, but then I'm very happy. Why? Because when I published the first one, Eleanor A, 2 months later appeared the first synthesis of Eleanor A. I said, oh my God, I have everything but the synthesis for that guy. What was the reason? He was working with coumarins. And in some way, you can imagine that the coumarin can be rearranged, open it, and then close it. And he said, in 2 or 3 steps, I can get it. And he published, I thought it was mine. He published the synthesis of this. Then I have another people that make a review of this kind of molecule. Unbelievable. It's a tetrahedron. It's a review, very nice review, okay? 95% of the publication was our publication. Unbelievable. And the third one is that I found at least 3 people in the United States in different options, and 1 in India, 4, that make the PhD working on this kind of molecule, synthesis of this kind of molecule. So I'm very happy, because when the science appear and it's not in your hand, it's in the hands of everyone, wonderful. It's because something is important. Okay, you know, curiosity. Okay, let's say, What we can do from now on? Good question, right? So, okay, there is any other possibility for extraction? Will we get the same compound if we change the methodology for extractions? Do it be better? It's important also. And of course, what application can we expect it in agriculture and drug discovery? It's a good question, right? Well, we try to look for supercritical carbon dioxide, as I mentioned before, and try to see, because we have a very good relationship in our university with the group that is growing up in this way. And by the way, the head, well, one of the member of this group from supercritical extraction now is the rector of the university, Casimiro, Professor Casimiro Mantel. Okay, so Professor Casimiro, he do the work with us here, and we do the supercritical fluid extraction with pure CO2, and then try to use some co-solvent, because we can use it, co-solvent of water, maybe methanol, and try to see if the solubility is different, okay? And also to say, okay, we can change the proportion with a hydrocolloid mixture and try to see if we can increase the number of compounds. So, again, we choose a collection and they choose 3 different ones, Stella, Arianna, Hillian, varieties, cultivar varieties, means that it's in the field. So every year it's growing in the field, okay? So using CO2, temperature, pressure, flow gene, and then the time. And then the best, they decide, okay, this is the best. So you have Stella, S, Stella, Arianna, Hillian, Hillian. So you can have good options here to have the best variety, Arianna, best yields in all conditions. Here. Okay, don't forget, this is bioactivity, okay? Bioactivity, again, you see 0, nothing is comparison. Down, inhibition, you have a large collection here, from here to here, so Stella and Arianna. Yield extraction, important, because it's important to know what is the percentage of the extraction. Don't forget that when you are talking about this kind of extraction, you really don't know exactly how is your solubility or the solubility of your compounds in this system. It's completely changed, okay? Supercritical condition is changing everything. So you must optimize, and you say, okay, I will take Arianna, supercritical extraction, fractionation of extract in cascade, and then increase the selectivity of the extract. That's the system. In this case, you have 2 cyclonic separators. You have first one, and then a second one here. So based on the temperature and based on the pressure and based on the flow that you are producing, you can have 2 fractions actually. It's like you have 2 fractions, different fractions, okay? But you can use co-solvent. If you put co-solvent here, you change the extraction, so you expect it, and indeed we got different kind of compounds here. That's how it looks in real, okay? And that's the extraction condition. We have conditional separator 1, 200 bars, 100 bars, 900 bars, 70, and for the second 1 bar, 1 bar, 1 bar, 1 bar, but we change the temperature to 45 to 40, 25 each one. What is the result? The result are we afforded 52 substances that belong to 10 different chemical classes. Again, are you crazy, Francisco? You know, don't accept impossible, don't accept anything. If you have an idea, please follow it, okay? Sesquiterpene-lactone, diterpenes, flavonoids, and so, that's the main one. And you have 17 sesquiterpene-lactone, new sesquiterpene-lactone, 1 sesquiterpene, 14 diterpenes, 2 triterpenes, 3 flavonoids, eleanols, apocarotenoids, coumarin, and lignans. But not only the new ones, against Fatima, look, alpha beta, but angelic also is alpha beta, contain an alpha beta receptor, okay? So, wonderful. Again, new kind of molecules, dimers, very nice dimers, actually hybrid, not dimers, hybrid. Hybrid between what? Between sesquiterpene-lactone, as you can see here, and diterpenes. So this kind of hybrid was the first time that has been published in Nature, and this is in the collection. Of course, what is the first question comes to your mind? You suspect, you say, oh, it is an artifact, because you change the methodology for extract. It is real there or not? Yes. This was our first impression, and try to see if we are convinced or not. Before I publish something, I do the same job that a referee. I'm a referee. I'm editor-in-chief of many journals, so I know what is expected, okay? But on top of those, I'm a scientist, and I want to be convinced that I say something that is real. So as I know, I have the reference. I was looking in a different extract system, in my different extracts, and was there. The problem is that here is clean, and the other one was hidden, was overlapped with other molecules in a small amount. So it was difficult to detect it, but now we detect it. So it's really produced by plant, okay? Well, let's play a little bit with the molecule. So what can you imagine? You have a dimeric hybrid skeleton. The name that we give it is helicaurinolites A and D. And this is a putative separation. You have this one, this one, this one, this one. And the stereochemistry was obviously established based on the noise effects, the noisy correlation for determining the stereochemistry of the molecule. And this is the plausible biosynthetic pathway. You have a molecule, nice molecule, but you have an epoxide. My friend, epoxide. Very active part of the molecule. This epoxide can be attached and open it. And you have an OH here. And then you can have minus H or minus water. If you have minus H, you have helicarinoids A. If you have minus water, you have helicarinoids B. This is a possibility, okay? And for the 3 and 4, you have a different way, because you have no epoxide, but you have the possibility to be attached here, because when you have this molecule in a protonated acid condition, you have a protonated DOH, so you have a positive here, the attach, and based on this, you can have this collection, helicarinoids D or C. Okay. What is the general conclusion in this part? For any phytochemical study, the selection of material with a certain type of bioactivity is critical. You remember, if I was concentrate not in leaves, but in flowers, only diterpenes. If I concentrate in different ones, leaves, many things. By direct extraction, including selection of the appropriate bioassay, important, and the appropriate system of extraction is crucial, okay? And once we have determined the active compounds, it is essential to optimize the extraction process, of course, because we want to be productive, okay? But let me think in bigger. Okay, I have a plantation, not thinking in Brazil because it's big, very big, very big. Let me think about a small one, like 5 hectares, not too bad, 5 hectares, big amount. We can do something with this or not. Maybe what we can do is just cut it, triturate it, and then leave it in the soil. Because the mulches could liberate these kind of molecules. So they prevent the loss of water, and they can prevent also the appearance of some weeds during the time that is nothing growing up. Then I put the new crop. New crop, I suggest, please, monocots. Why monocots? If you go to Mexico, you can see many fields of maize, corn, okay? Milho, I don't know, milho, Brazil, okay? And you say, oh, there are many, wonderful, beautiful. But some of in the middle, you can see some flowers appear. Elianthus maximilianus. They have a taller than me. It's about 5 meters sometimes, 5 meters tall, okay? With 2 branches, not only one, 2 branches. Oh, wonderful. Okay, and I was asking to my friend, what are you doing with this? No, we don't touch it. I mean, we leave it there. Why? Because they remain clean, the field, for any crop that can try to establish during the crop growing. So for a monocots, these dicots help to avoid any dicots attack. Unbelievable. Now we know why. Okay? Okay, Oryza sativa. Oryza sativa rice. You say, oh, wonderful, wonderful. I have a lot of rice. We have a very nice production in Spain, particularly in Seville. We call Isla Mayor, Isla Menor, minor island, higher island. Okay? You know the system for production of rice. Usually it's underwater. So you have plenty of water, and in that place in Spain it's very flat, so it's very simple. You just dip contain of 25 or 50 kilograms of seed or rice, okay, dip in water, go to the plane, and then you go to the plane and spray the seeds. That's it, simple, okay, very simple. But you have areas like this. The problem with Asia is not the production itself. The problem in Asia is that there are not only one crop. They use 2 and 3rd and sometimes 4 crops in the year. Of course, the first one is okay. Second one, yield is so-so. The third one and the fourth one is just for me. Just a couple of rice. That's it. Not too much. It's one of the more important, as I mentioned in the world. Okay. So you take the plant, rice plant, extract, fraction, pure compound, bioassay, and then structure activity relationship studies, and you find mainly that you have carotenoid degradation compounds, bisketterpenoids, compounds with phenolic nature, diterpenes, 2 fatty acids, and 12 esteroids. But say of pure compounds here, and you have mainly esteroids. Steroids, you say, okay, steroids. It is important to have steroids, yes. You know Danacol, I don't know if here is the same name or not. Danacol is a preparation that you can take it with a lot of bacteria, very well for your stomach, okay, but also reduce the concentration of cholesterol, okay, they call it. And now they also sell it for women, particularly for women, if you are in the age of the menopause, because they help to control the production of different steroids and different hormones. So cholesterol, I mean ergosterol, beta-acetose, 7-beta hydroxysteamasterol, and so on, so they can be taken easily from the rice production and produce something as a bioproduct, because the main production, of course, for proteins and for edible plant. You know that usually in Asia, they say that if you have a cup of rice every day, you can survive your whole life. So it's enough, because it's a very, very complete combination of proteins, vitamins, and so on. So it's very, very healthy. Now you know that also it's very healthy since the point of view of cholesterol and so on. Okay, number 7, number 105 and 11, they have IC50, listen, 7 micromolar. 7 micromolar, this is almost nothing, very small amount. Okay, now I'm going to superstars. Let's go to superstars. Why Graminae, maize, rice, and wheat? It was a big project that we started in Europe. It was a big European project where we are looking for something that was very known by that time. What we know by that time was, okay, we can have BOA and DIMBOA, those alkaloids. And we say, it's easy. It's easy. Francisco, you have experience, go to the plant, make a separation, and give us references for all the group. We are 25 different countries working on this kind of molecules, and I would provide all the standards for everyone, okay? And they want to have a comparison between the winter and the summer crops in different parts, in the north of Europe, Central Europe, and Southern Europe. Okay, if you look in the literature, you see, okay, by that time, you say, okay, Francisco is very easy because you have only this molecule, diboa and dimboa, but usually in the plant you have a glucoside form, and then you got this. And I say, well, maybe we need to have also glucoside form. Yes, we need it, okay, but you have a problem. Because when you try to make isolation of this, because it's released by the roots, okay, they make hydrolysis immediately. So you must work very quick and try to avoid the hydrolyzation. Okay. Even more, we have the low stability of benzoxathinoid is a very well-known phenomenon, because by that time we know that they can be modified to a 5-member rings, also aminophenol, and then something else, we don't know by that time these two. Now we know for sure that they are APO, this one, and the acetate APO, and the same with BOA and dimboa, the same one. Benzoxathinones, benzoxatholinones, aminophenoxathines. So the plant is producing one kind of molecule, but the fate show you that the final one that you have are aminophenoxathines. And listen, this is also something really interesting. If you are working with diboa, which is this one, okay, diboa, what they are is an age, okay, so this one, diboa, the half-life is 28 hours. So every experiment, any experiment you want to set up, including animals, including insects, including plants, of course, more than 28 hours longer is not anymore there, should be degraded, okay? But what happened with dimboa, even worse, because it's only 31 minutes, almost nothing, okay? So what are you looking for in the bioassay? Remember I mentioned, please ask the right question, okay? What happened is that we try to see the bioassays for the BOA glucosylate, the BOA, APS, aminophenol, APO, aminophenoxathine, and AAPO. And what happened, as you can see here, is the APO is the really very active compound. But AAPO, when you have acetylation of DNH, completely change the story. You say, hey, what happened here? Maybe it's a wrong answer or wrong question or what? No, it's very simple. You have a plant, which is the donor. You have a plant, which is a target plant, okay? The compound are released into the floor, to the soil. In the soil is make a transformation. They produce APO, and they go to the target plant, okay? But the APO remain there. So even the production plant can absorb. When they absorb it, what they do is just make an acetylation and inactivate the compound. So it's not dangerous for the plant that make the original BOA or dimboa. It is really important. Why is important? Because as I mentioned, we can do genetic transformation. So maybe what we can do is to apply APO in the field to control any problem, okay? But what I can do is just to introduce genetic modification, given the option for the crop to make acetylation of APO. So it's a very natural and simple way to use transgenic molecule that is quite different that they are doing until now. Okay, cluster analysis, they give you an idea about Logran, remember, is a positive control, and then you have APO, BOA, the other ones. APO is the best, of course, and so on. Well, we try to look for optimization and try to see if the phenomenon how is. Donor plant, pre-germination time, we try to seedling density, optimal time, and so on, and to prove, you know, I'm a scientist, I mentioned. A scientist is make a difference between a scientist and people that want to talk many things without nothing, is because I can measure. So I say, if nobody can measure, how you detect that one product that has been produced by this plant has been absorbed for this, make a translation, a translocation in the other one, means nobody by that time was proving that allelopathy effect occur since the chemistry point of view. Okay, so we make this kind of design. We try to look for group and try to see what is the evaluation of what is the dynamic of production of the VOA in the plant since the every day of germination. We can see the effect in order to establish what is the time, the right time to be in the field, because I tell you, it's not only to have the potential to control something. To control something, you have a component which is the structure, a second component which is solubility, third component is stability, and the fourth component is for how long are you there, okay, before degradation. Because if it's a natural compound, every time, more or less, could be degraded. Okay. So, we try to choose the dose response of Avena fatua with Secale cereale and try to see what is the best point to establish the density of seeds, because we want to have a crop and try to see how is the evolution of those. We check it, we test it, and we have the condition, 300 seeds, 12 days of growth for germination, means that as soon as they are germinating is incorporated in the system, in the field, the amount of compound that we needed. Actually, we have the BOA and APO, and the number of seedlings, Secale cereale. You can see how is the production. So we have an idea about the number. So let's try to see. In this case, we use 600 megahertz to make analysis, and with the diode array and NMR. You remember the picture yesterday? A couple of minutes ago. You have the NMR, the HPLC, the MS there, and everything is under. So you just detect it in the UV, stop flow, split. Part is for the NMR, part is for MS. Okay, everything in the same room. This is because are binded. The magnets are binded. Okay, so 600, but actually is not affected everything that has less than half a meter. So you can put there everything without problems. In other words, this is the scheme. So you have a donor plant. We measure the donor plant since the early beginning, in the leaves, in the stem, and also in the roots. And we know that it's producing in the leaves, making anhydroxylation, and glucosylation, and then go through here, then go through the field, liberate, prepare APO, and then what the target plant receive is not only a single molecule. It's the consequence of the time and the cocktail, the right cocktail. Now we know, because of the degradation time, we know the cocktail that usually arrive to the plant. Okay. So we have demonstrated that is taken out also here, and we can see it was able to see the effect in the target plant. Okay. This was the first time that has been demonstrated its concentration inside the plant is not conclusive, meaning if the plant can produce half a gram but is not liberate, it's not conclusive. So means that allelopathy is a dynamic phenomenon. It is important. Until now, the target plant has been never chemically analyzed in the search of allochemicals, and its degradation product released by the donor. And it is important, the analysis to analyze the fate is important. The fate of the study of allochemicals and their ecotoxicity on the flora and fauna. Okay, let's say none of the different parameters are static. The phenomena are extremely dynamic and time dependent. The bioacid conditions affect those variations. The chemical nature of allochemical cannot be controlled in physicochemical. Its physicochemical properties determine the persistence and integrity. I tell you, first, solubility. Second, degradability. Important. it is a clear evidence of the existence of allelopathy. So every time you mention that allelopathy phenomenon exists, please refer to our publication. It was in Journal of Agriculture and Food Chemistry. Okay, let's move to Tectona grandis. Tectona grandis is a very nice plant. You know Tectona grandis, what it is? It's a large natural tree, Southwest Asia. It is highly appreciated for quality of woods. Why is appreciated? Because if you are furniture that are outside, they are very resistant to oxidation and also very resistant to fungi infection. So also is used sometimes in the water. I'm sorry, the water in the bathroom when you have a shower, okay, and you put some wood in the back. So it is resistant, waiting very well. Okay, the name, the regular name is teca, the teca.
We have it in north.
North, yes. This is very popular also in Cuba, okay? And actually they have a system that they call tangier. It is something that they call here in the middle. You have the tree, but in the middle you have some crops that can co-crops, okay, controlling. Okay, so we found here many things. We found quinones, naphthoquinones, diterpenes, lignans, terpenoids. But the queen in this case of the story is naphtotecton. Naphtotecton A is unbelievable in amount and also in bioactivity. Naphtotecton A is the most abundant active compound and clearly contributes to the allelopathy phenomenon. This new quinone is proposed as a model, and we'll see what we can do with this model. So this is the part 2. I will explain part, how many, 15 minutes more or less?
Yes.
We can start with parasitic weeds, and then we can go for the other part, okay? Which is very intensive. Please be careful because we are going to more chemistry, okay? So part 2, we are talking about 2 things. One is manipulate the ecosystem, but parasitic weed species, okay? Chemical signaling hunters. Then I will go to search for herbicide models in field, okay? So we will go through SAR activities, structure activity relationship studies, and nano-encapsulation, and how we can use both of them in field trials. Okay, I don't know if you are familiar with parasitic weeds, chemical signaling hunters. They are beautiful, they are so beautiful. This is the plant, but this is the crop. Oh, if you look closer, you have here some lines. What is the problem? It's very simple. The problem is you have hemiparasites that can photosynthesize and survive without their host. Okay, fine. But mainly you have holoparasites, cannot photosynthesize and do not survive without their host. Means if I want to survive, I must to catch it and use it. Okay? This is the case of Orgânica cumana. Important, this is important. They are highly resilient. They can wait until 10 to 20 years waiting in the field, in the soil, just to find the right time. Okay? And when they start the germination, that's the question. When they start? When they receive the signals. What kind of signals? Signal that has been produced by the hosted plant, potential hosted plant. Okay? Those compounds are the one that we call germination elicitor compounds. Important also, not everyone is parasite, everyone, except one, Paragynca ramosa, is the most promiscuous parasitic plant because can parasite whatever. Okay? Doesn't matter. The other one, no. Cumana is only for sunflower. Mino is only for haba, for tobacco, crinata, for ramosa, Egyptiaca. So they have specificity. Okay? Oh, interesting. This is a sunflower. Wonderful. Orgânica cumana. You look closer, you see here. Listen. You can see this beautiful plant here. I'm sorry, too late. Everything is infected. Too late. What is the problem? The problem is the following. They are the seeds here, okay? They are the seeds. Okay, the seeds are starting the germination. When they can detect it, the presence of the signaling there. I mean, a plant that can be hosted. Okay. So as soon as they detect it, they start to grow up. When they start to grow up, they produce this one. They produce haustorium. Haustorium is like a branch or like a tube. Okay. It's touching. You see the hosted plant. This is the tube. Touching the hosted plant. As soon as the haustorium is there, it's touched, they start to catch all the nutrients, everything they need, okay, because they can produce it. So they have no roots, so they are take it, okay? And they grow up and grow up and grow up. They saw this beautiful plant. And say, oh, this is so beautiful. Completely infected, okay? And they produce thousands of seeds. This is the second point because they survive. Second of seeds that they are going to the soil. So you try to harvest it, you have tried to remove. No. They are there. Okay? So what we were thinking, okay, what we can do? You have, it's difficult to control, traditional method for other weeds do not work. Hand weeding, of course, is one of the options. Crop rotation, pesticide, but indeed it's not working very well. Parasitic weed cycle is the key to solve the problem. This is our point of view. Why is the key? It's the key because you have different structure. The most known are strigolactons. Strigolactons. So they are detected, they start the stimulation, they start to grow up, and those strigolactons are molecules like this, strigol, okay? So the most abundant germination is here. Actually, it's a plant hormone, okay? But obviously, I produce the plant hormone by myself to help me. To help me what? Branch it in the aerial part and also in the roots. Not for give any signal to the parasite, okay? But anyway, it's there, okay? And it's detected. Listen, can be detected at 10 to the minus 12. Unbelievable. Can be detected very little. Okay. So the plant hormone for the plant architecture, arbuscular mycorrhiza, and so on, is ubiquitous to the plant kingdom, germination elicitor of parasitic plants. Strigol is one of those. By the way, beautiful Michael addition, Michael receptor. Again and again. Again and again. Well, so what happens is that you have Striga hermontica, Horticula cordata, you have the root exudate, stimulate, you have a Vigna ungulata, Orobanche minor, you have a stimulate. They have several ones, different ones. Strigon, Alectrol. So it is not only selected because the species, it's because the plant that is producing different kind of signaling. Okay? So in the case of sunflower, we have something else. Why? Because we have in the root exudate, listen, root exudate, remember this one? Costunolide. The dihydrocostunolide, custulacton. Can you tell me how polar is this? How polar are those compounds? Almost nothing. Very, let's say, you can solve it in sometime, of course, dichloromethane and so on, but not too polar. It's exudate by the roots. Okay? So they make a stimulation of Orgânica cumana. Sunflower, Orgânica cumana. So what means is that sesquiterpilactone have also anti-inflammatory, phytotoxin, cytotoxic activity, of course, and those are, as I mentioned, one of my favorite. So what we can do? Sometimes the people was taking the name of suicidal germination. It's a strategy that they say, okay, they will start with the strategy, but we change the name for honeypot strategy. Why honeypot? Because they never can refuse. I mean, I make a proportion of one of the compounds that say, okay, that's the time for stimulation. They start, they grow up, they start to germination, okay? They start the germination, they start with the haustorium, and what happened? No plant can be hosted. They can survive only 15 days. Between 12 and 15. After 15 days, they can survive. So, what is a question to apply, wait for 2 weeks, then remove it. Apply, wait for 2 weeks, and remove it. So you can clean it up, the seed bank reduction considerably. This is not a voluntary act, of course. It is a trap, and we really offer something that is impossible to refuse, as I mentioned. Okay, so that's the name that usually today is used for this strategy, honeypot strategy. Okay, so what we can do? Let's go to estrigol and some others. You have a plant hormone affecting soil microbia. The presence of several chiral centers means a costly synthesis. Of course, you can imagine. They suffer degradation after a certain time under solution in aqueous media. Difficult also to establish. So what we can do? We have a standard that has been used for many years with GR24. It was Professor Swanenburg from Netherlands, the one that made the first synthesis of this, and then was using some mimics like this, analogs, 4 bromo mother broms like this. So they contain the D, but not the other ones, okay? So the analogs. You can have analogs and mimics. What are analogs? What are mimics? Analogs preserve the anon unit connected with a butanoid, okay? But the mimics don't need it. Something different. We'll see. Okay, we have sesquiterpilactone. We are chemists, organic chemists, so we can do is something like it. We have the hydrocostolactone. We can produce Guayan strigolactone because it's a guayanolide, okay? Guayan strigolactone. And we are synthesizing these kind of molecules. They are analogs with activity toward Pelipanchi species. The alpha-methylene gamma-lactam moiety, considered the key for germination and other biological activities, are there. 1 and 2. I remain 2. Okay? Synthetic path guayanostrigolactone. Okay? We have this, but we can start for this aldehyde that comes from an alcohol. The alcohol could be protected and then liberate, or starting from the single molecule. We can use, based on the hydrocostolactone, we can use this or this, without double bond or with double bond. Based on costunolide, we can have eudesmanostrigolactones. Okay, we have costunolide, and in the chloromethane with toluene sulfonic acid, you have the possibility to make a cyclization and pass from germanolide to eudesmanolide. And from the eudesmanolide, you have also 2 options here, 60%, 58%, with double bond intra, double bond, exo double bond. Okay, with DBU, with the basic condition, you can have here an addition to the molecular addition here. With DDQ and dichloromethane, you have a OH, and then aldehyde, and then incorporate the new system to have eudesmanostrigolactone. Okay, from each eudesman, it's possible to obtain 4 eudesmanostrigolactone because you have double bond and you have another chiral center here. So you have 4 combinations, okay? How it looks? Bioassay is very simple and complex at the same time. Simply because it's a question only to have under a microscope to see how many seeds are germinated. That's it. So we choose Orgânica humana, minor, Aegyptiaca, Ramosa, and we choose in the microscope. The same again, we take a picture, so it's not a question to accounting by your eyes, but also by the machine, okay? So it's complicated because you must to sterilize the seeds, use the disc, and use the pre-treatment for 3 times, and the seeds with an immersion radical through coat scored. If they are more than 3 millimeters, can be accounted. If not, we consider that it's not germinated. And this is how it looks, the bioassay. The bioassay here is at the opposite way. Everything is a stimulation, so everything equal to control, 0, but stimulation, so up. The lines should be up. If it's down, you have no stimulator. You have inhibitor, so no, doesn't work. So you have here GR24, which is a standard, 9, 10, 15, 16, 9, 10, 15, 16, and it's a question to see how is the stereochemistry of the double bond. It's important, the stereochemistry. It's a very, very nice system, depending on the stereochemistry. You have Orgânica cumana, and you have also selectivity. In this case, the number 9 is almost nothing, but this one, 10, 15, 16 is working. Orgânica crenata, you have 9 is more or less working, but the other 3, almost nothing. So Strigolani, now we are moving to a second family of compounds, mimics. And we say, let's try mimics with using thalamides. Why thalamides? Because we know that thalamides breaks the dormancy of celery apium graveolins in a similar way that gibberellins. So means it's in some way it's kind of a stimulator. Gibberellins, you know that is also phytohormones, okay? So cotylamide, strigolactone increased cotylamide production in cotyledons, and the imaging one was by my friend in Zwanenburg in Netherlands. He prepared an imaging one, this one. Okay, we say let's try something different. We choose this one, number 4, and we try to prepare, like we prepared already, this set of molecules. PLO1, 2, 4, 6, 7, and so on. We tested, and we see that it is working very well. And indeed, you have a very good percentage here, 52, 59, 33. So we can produce in large amount in a very effective way. And the question for us was also racemic, because there are 19 racemic and substituted thalamides were taking in parasite germination here. But the racemic in this case also work. Orgânica minor, Orgânica cumana, you will see here. The different functionalization of the chain site affected activity. This is important what is here, chlorine, amide, or any other. Position 4 was favored instead 3, it's important also. And some compounds were significantly active in both species. Okay, Pelipanchia hessiaca, Pelipanchia ramosa, you have also a collection. So as you can see, we have a very nice collection of mimics that can be used for parasitic weeds. Well, we face the problem that we face every time. We have nice molecules, wonderful, but soluble in water, sometimes they are not soluble in water. So we need to be soluble in water because they are affecting the transport in site action for physiological aqueous medium to remove from the soil for irrigation with water. So what is the strategy? You have at least 2 strategies. Actually 3. One is chemical modification of active compounds. So I change literally and produce salt rather than acid, basic, or whatever. I can use some little portion of solvent or coadjuvants in the formulation, like dimso, for instance, but also they can affect it. Dimso, methanol, acetone, they can affect it. Or another option I want to show you today, it is nanoparticles and encapsulation. nanoparticle and encapsulation. Okay, so let's start for the more simple things. Cyclodextrin and nanoparticles. Reducing the size of compound's particle or enclosing inside the soluble capsule. Keep the structure and modify. It's important because we don't modify the structure, but the question is, should be inside, not outside. Okay? So we have alpha, beta, and gamma cyclodextrins. Advantages and disadvantages. Low cost, alpha. Non-toxic, beta. And soluble in water, gamma. So we must test everyone. Okay? They have been applied successfully to pharmacological molecules and so on. And also important, the human consumption of cyclodextrin is authorized. In Europe, beta cyclodextrin is a dietary product. So we can eat it. So it's important also. Well, doesn't work. If we check, you have sesquiterpilactone of non-biological activity, phthalimide, active in parasite and wheat, dihydrocostostrigolactone, and we have solubility of the complexes, stoichiometry, theoretical calculation, and then biological profile of complexes. Okay? In this case, what we do is very simple. It's just cyclodextrin and guest, solvent for homogenization, then recovering, then drying, and then solvent evaporation, complex precipitation. You have the his, and then finally cyclodextrin. So you have two options. We tested both, and we have the lowest increases in alpha cyclodextrin. The highest increase was beta and gamma in this ratio 2:1:3. And similar solubilities heading in the co-precipitation. So we know the way to produce it, what is the more efficient, and what kind of cyclodextrin is the one that we needed. So we have the solubility here, and this is also very nice. The increment of solubility was up to 190% in PL01. So it's a lot. So what's the meaning? First one, you don't need to put any coadjuvant, any co-solvent, nothing, just water. Is important. But not only this, also they increase the availability. Okay, we make the calculation with the alpha, beta, and gamma, with the theoretical calculation of the complexes, and the semi-empirical with docking and so on, PM3, and in this case on PM3, and including 250 water molecules to consider solving efficient. You have here with 1 beta, 1 gamma, 2 beta, 2 gamma, 3 beta, 3 gamma, and we are making calculation here. Try to organize how is the distribution in the space. Okay, this is for PL01, but this is for PL07 with chlorine, and we check also how was the aromatic ring influenced. You can see here the aromatic ring is outside of the crown. It's like a donut, and outside is facing the chlorine in this case. Okay, all the compounds were tested. All the compounds was used, but in this system, without solvent, without organic solvent. Okay, so this was really very, very nice experiment. We increased a lot. Also another thing, you have here the empty cyclodextrin, the full cyclodextrin, and the complexity in different ratio. So you can see here how the stimulation was really very high. Okay? In the Orgânica ramosa, here also the stimulation was very good. And finally in Cumana, you can see higher 24, but the 13 beta ZD is okay, but the 12 the beta CD is also very good component in this case. So racemic mixture could be used. Active height even at low concentration, 1 micromolar. Sun can stimulate 4 different parasitic weeds at the same time, which is also important for us because the bioassay could be generalized. There is a dependency of activity with the chain size, and the log P means that you need to make some help for solubilization. GA3 did not stimulate germination, so it is not needed to use, and the activity of GA3 is depending on the stereochemistry, so I think in this case it's not crucial. We designed a simple and effective and economic way to use it with cyclodextrins. In some cases the activity was sensitively increased. I'm sorry. The encapsulation increases solubility over 25, in case of encapsulation with nanotubes in 5 times, and the activity is maintained with encapsulation, almost increasing. Okay, that's the structure-activity relationship that we want to show you, but I think this afternoon. Okay, thank you so much. Any question? That's the time.
I forgot one question this morning when you were asked about in your chromatograms, did you use some acid or something, because she mentioned something she really likes, it was really nice, like some additives.
Additives.
Additives, yes.
As I mentioned, I try to avoid any additives. Any. Usually what we do at the beginning was DMSO in 0.5 percentage, but I try to avoid, because DMSO also is a hygroscopic, so it's taking all the water in the media, so it's very problematic. If you can avoid it, you can not use it, much better.
That's my question. So in your presentation in Eliantus, you mentioned the extraction using CO2 supercritical, right?
What? Use?
CO2.
Oh, yes. Supercritical conditions, yes.
But you didn't mention how do you isolate it, or if you just got those compounds in one step.
No. You have 2 cycles, okay? And you can take as many fractions as you want based on the time that you are spending.
I got you.
Okay? So you have 4 fractions, but the polarity is nothing in comparison with the previous one, because you have solved it. I mean, it's not a question of solubility based on the polarity. It's a question of solubility of the compound in the system, because CO2 can solve or not. It's quite a different story. Okay? So sometimes in one of the fractions I isolate only 2 compounds. That's it. In large amount.
Nice.
In large amount.
I've never used it actually.
I tell you, it's very nice, because you have this rotor, okay, and then you depress, the pressure of the CO2 disappears. It's totally clean. No solvent, no any residue. Just the compounds that are in the mixture, of course. Sometimes 1, 2, 3, or 4. You know, it was inspiration. Why? Because we are studying sometime 1 or 2 components, basic components on beer. When you drink beer, okay, one they call it ACE, beta ACE and alpha ACE belonging to the beer. Those are active compounds that they are making regulation in many places, okay? Based on the concentration of these 2 acids, you can be allowed or not to use this beer for a normal drink, okay? So it was very nice, because they set up the calculation and so on, to make in one vial alpha, another one beta, at a certain time. So I say, well, could be so specific. Why not in a regular plant? And actually my friend, the actual rector, is not only using it for me, of course, for sunflower. They use it for mango, they use it for many things, to select 1 or 2 major components. It's very precise, as soon as you know, of course. At the beginning you have no idea, but you must do first, optimize, as usual. Pressure, time, temperature, and flow. Okay.
More question? I have one. When you talk about carotenoids,
Yes.
what means this name? That compound came from carotenoids, degradation of carotenoids?
Correct.
Oh, yeah.
That's correct. That's the origin, yes.
Okay.
And the people choose apocarotenoids.
Yeah.
Yes.
The question in the people out here. Só isso que você não... Tem perguntas com o pessoal fora?
Tem. No chat tem.
Yeah. Sim.
Pode ler? Quer ler? Não, você não achou. Could you advise on what is the best extraction strategy to minimize the degradation of the unstable benzoxyanoids for mycelium metabolic studies?
Okay.
Could you follow with that?
Yeah. It depends. When you are thinking about the best extraction methodology, okay, in this case, benzoxyanoids, it depends if you are looking for the base compound, the aglycone, or the glucoside form. If it's the glucoside form, I will try, and I think it's something that we can do in the near future, because we need also some time as a reference, the glucoside form. I will try also with supercritical condition, because they definitively avoid any kind of degradation. It could be very fast, okay? But if you are looking for the aglycone, mean BOA, DIVOA, and so on, normal extraction is okay. I mean, it could be normal dichloromethane. Actually, we have several publications I put in the presentation. If they can choose there, they have the methodology for the extraction, or the standards, yes.
Quem fez a pergunta não tem aí?
Foi a Jéssica que perguntou.
Quem?
A Jéssica.
Ok. Você falou que era Jéssica? Ok. Jéssica is a student here.
Okay.
Postdoc.
No, okay, fine, perfect.
Ela continua a pergunta. Another question. The component BOA is not formed as a natural metabolic
Mais, yeah.
Does the reaction occur only after it's released into the soil?
No. BOA is produced. I mean, BOA and DIMBOA are the major compounds. They are produced in maize. But the major producer is not BOA and DIMBOA of maize, from maize. It's from barley. They have large amount. And also, I will tell you something. APO, which is let's say one of the key points, aminophenoxathins, it is very stable, but not only in the soil. Also, if you eat some bread made with some barley, not only barley, but some barley, or maybe with some maize, or maybe with some wheat and maize combination, we found APO there. So it's very healthy. I recommend it because it's one of the main compounds that also are used for pancreas cancer, to prevent pancreas cancer, okay? And also, if you are making a fermentation and you produce this kind of yellow liquid beer, okay? In the beer, if they contain some wheat or some barley or any other, could be also present there, the APO. The question is the amount, okay? So the stability is something really relative. If it's in the mixture, it could be more stable than never. In the soil, 3 months could be stable. 3 months could be remain there. Yeah. You have
More questions? Yeah.
What's the other reason for using the materials to encapsulate this substance? And in your experience, after this substance has been used and tested, is there a frequency of using other materials to improve the potential use of the substance as herbicides?
Yeah. If you wait until this afternoon, I will give you the answer. Because I tell you, the last point was, or the second point was nano-encapsulation. Okay? And I'm chemist, but I say, well, nano-encapsulation. Okay. What is the difference between a chemist and a people that is making formulation in the 14th centuries or something like that? because you know what you want to do. The other one was just, mixture this with this and we'll see. we have a Spanish word for that, pucherología. Means you want to cook, put something in the place and put everything together and we'll see. If it's something good, I take it. If not, I leave it, okay? So with the nano-encapsulation, I was very accept. Because, firstly, are you sure that it's there? Secondly, what kind of nanoparticle had you produced? Third, is it stable enough? Four, do you have an idea about the amount of active compound that you have inside? 6, do you have the possibility to control the liberation of the active compound in the place you want it? You will see. Okay?
Okay, thanks a lot.
Thank you. Thank you.
We start the second part of the course.
At what time? What time, Fatima? At what time?
Ok, 2 o'clock. Em português, para vocês vão almoçar aqui, tem restaurante aberto, como eu comentei, tem um evento. A gente pode...